Economics. Thank you for joining us today, sir.
Thanks for the gentle introduction, Professor Agnieszka, and thanks for the organizers to have uh, invited me for this talk. I'll be talking today on design of revenue optimal options in two-item setting. And here is a brief overview of the talk. So I'll first be introducing the auction setup, and then we'll be giving you the results that are already available in the literature on the one item and the two item settings. Okay. And then I'll move on to our work, where our work is on two item setting as mentioned in the title of the talk itself, right? And so I'll first start with what we did in the uniform distributions, then for distributions with positive power rate and distributions with negative power rate, and then finally summarize the results. Fine. So let's get started with the auction setup. So auctions are something that we are very familiar with, right? So I mean, we have seen a lot in cinemas, right? Someone with the hammer and say order 1, order 2, and all that, right? So here we are actually considering a very simple case where there is an auctioneer who is selling only one item to one buyer, not even multiple buyers. There's only one buyer. Okay. So you can, instead of considering it like an auction setting, you can consider it like a shopkeeper. The auctioneer can be like a shopkeeper, for example. Okay. Since there is only single buyer, and you're a buyer who's going to buy a single item. Okay. The setup is the following. The buyer actually has a valuation. So I think from Rajiv, we have heard this word valuation already, right? So it is the value that you have for the particular item. Say, let's say you're going to a shop to buy a pen. Okay. So you have a value in mind. Okay. So I can pay, let's say 15 rupees for this pen, right? So that's the valuation the buyer has, but the valuation is known only to the buyer. It is not known to the seller. Okay. If it's known to the seller, he can just quote the price. Yeah, that's the price, and then we are done, right? So the buyer knows this, but the seller does not know it. Okay. So, but what does the seller know? So this valuation Z is actually picked up from a distribution F, and this distribution is known both to the buyer and the seller. So this is actually a common knowledge. So it is something like, yeah, of course, the shopkeeper does not know that your valuation is 15 rupees. But what he might know is that, see, if the pen, if he sells it between 10 rupees and 20 rupees, okay? So, I mean, he knows that the buyer is likely to buy it, right? So that knowledge is modeled as a knowledge of the distribution, okay? And yeah, so we assume that this, the support set of the distribution is between C1 and C1 plus B1. Okay, C1 is the lowest possible amount, and C1 plus B1 is the highest possible amount. Okay, right? So yeah, so we want to design an auction, okay, that satisfies certain properties. Okay, and so one of the properties is that the auction must be designed so that the buyer reports his valuation truthfully. So this property is called as incentive compatibility in game theoretic parlance, okay, or strategy proof if it's in more general context, okay. And the other condition is that the buyer must not be asked to pay more than his valuation, right? So if his valuation is 10 and you ask him to pay 20, so he would feel that, yeah, I would have rather not participated in the auction, right? So that's individual rationality or voluntary participation, okay? So yeah, under these conditions, we want to design a revenue optimal auction. What does that mean? We want to maximize the expected revenue, okay? But I mean, when I say design, what do you mean by designing an auction? So as I just said, auction just means taking a hammer and saying order 1, order 2 and all that, right? So that's only one kind of auctions, right? So there are many kinds of auctions that are there in the literature. So in any auction design, okay, what you're expected to do is to design an allocation function Q and the payment function T. So that is for each value between C1 and C1 plus D1. So suppose it is between 10 and 20, okay? So for any value that he is going to say, so he might say 11.7957, okay? So you must design a Q, that is the allocation function, that is the probability of allocation to the buyer, and the payment function, what is going to pay, yeah, right? So yeah, this is basically the setup. Now we will see what is the so-called optimal auction. Okay, so in the one item setting, and so we are only considering the one item now. Okay, so yeah, this is basically the optimization problem that we are solving. Okay, we are maximizing the expected revenue, which is max of expectation over T. T is the payment that is made to the auctioneer, right? Subject to these two conditions, incentive compatibility and individual rationality, right? So you can see that this is actually a functional optimization problem because you are searching over two functions, the allocation function and the payment function. Okay, so it's a functional optimization problem. And so functional optimization problems are much harder because the decision variable itself is a function, right? It's not just a few variables, right? But fortunately, this problem has a very simple result. Okay, and Myerson solved this problem in 1981, and this is for any distribution f. So given that f is known, okay, so you can solve this particular problem very easily. What is the answer? Find this quantity p. Okay, p is that value of z which maximizes z into 1 minus f of z. Okay, a capital F is the cumulative distribution function. Okay, so the item is allocated if the buyer's valuation is at least p and he is asked to pay p rupees and he's not allocated the item otherwise. Okay, so I mean, I think this diagram represents what is required. That is, if so, the valuation can be between C1 and C1 plus D1, right? So if okay, that should have been P. It's not P. The one in between is actually P. Okay, so if your valuation is to the left of P, that is less than P, okay, you are not allocated. If it is P or more, then you're allocated and what you need to pay is P rupees. Okay, it is actually a simple take it or leave it offer for a reserve price. So what the shopkeeper has to do is that he has to say, see, this pen costs 15 rupees or 18 rupees or whatever. Okay, so whatever the reserve price is, it costs P rupees. Okay, do you want to buy it or not? If your valuation is less than P, you say, okay, this is too much and you go away. Otherwise, you pay that amount and buy it. Right? So this is the solution for any distribution. For whatever distribution F you give, the reserve price may vary, but this is the mechanism. Okay? Yes.
Like as in the example that you mentioned right now.
Yeah.
You can't cross that P also. So you should actually be there in the less than P and we should have a one small P as the form.
No. So let's say it is between C1 and C1 plus B1 as mentioned here, right? So where is that? Yeah. So the P will be somewhere in between.
That is
maybe say C1 plus D1 by 2 or something like that. I'm just giving an example. Okay. So if his valuation, which is that Z which is only known to him, right? It might turn out to be less than P, for example. In that case, he will not buy it. Okay. If it is more than that, he will pay that C1 plus D1 by 2 or whatever and get that amount. It could be much greater. So it could be C1 plus D1 also. But he just pays that C1 plus D1 by 2 and then he buys the object.
My
Question
concern
is,
my concern is that P is not known to the buyer.
no, P is this. So if the what is that? The auctioneer wants to maximize his revenue, this is the P that he is going to do. So even the consumer can calculate this if he wants. Yeah. Okay. So yeah, fine. I mean, I'll just give one or two examples so that it makes this one item setting even more clear. Okay. Okay. So let's say the most obvious distribution that everyone takes, right? So the uniform distribution is 0, 1, right? So in that case, capital F is Z, right? So what is the maximum of Z into 1 minus Z? It is this parabola curve, and the maximum is half, right? So if the distribution is known to be uniform in 0, 1, so what the auctioneer has to say is that, see, this product costs half a rupee. So do you want to buy it or not? So if the buyer gets the item for half, if his valuation is more than half, otherwise he doesn't get the object, he walks away. Okay. So a small intuition on why we should set half, right? So why not set 0.9, for example, right? So if I set 0.9, then for each time the object is sold, I'm getting 0.9, right? So why should I stop it with 0.5, right? So yeah, it is true that I get 0.9, okay, when I sell it, but the key is when I sell it, right? So the probability that the object gets sold becomes very small because it's uniform in 0, 1, right? So that means if I quote a price 0.9, the probability that the object gets sold is only 0.1, right? So you can see this expression Z into 1 minus f of Z. Z represents the amount that I get when the object gets sold, and 1 minus f of Z represents the probability of the object getting sold, right? So if you increase Z, say to 0.9, for example, okay, so yeah, your Z increases, but 1 minus f of Z comes down, okay. Similarly, if you reduce from half, let's say you reduce it to 0.1, for example, okay, your 1 minus f of Z goes up, right? So that's because, yeah, so if you set the price to be 0.1, then you're selling the object with 90% probability. So 1 minus f of Z goes up, but Z comes down. Okay. So this expression, whatever you see here, Z into 1 minus f of Z, is actually a trade-off between the amount that you get when the object gets sold and the probability of the object getting sold. Okay, so that's how it turns out that, I mean, the expression is so nice. You choose that Z for which Z into 1 minus f of Z is the maximum. Okay. So yes.
The seller is getting the P.
Yes.
So I think it should be a function of the knowledge of the buyer. So if the buyer is ignorant, like in an auction house, suppose somebody is selling the items from antique. So there may be two classes of buyers. In one class, a buyer may be ignorant, and then the seller has more leverage. He can set high P. He can expect the buyer to pay highly, even when the product doesn't deserve it, because the buyer is ignorant.
Yeah. So
buyer may set high P even for an item which doesn't deserve that high P, and the seller can leverage on it. So maybe that seller can also put one parameter to take into account the knowledge of the buyer. Right? So suppose when we go into market to buy something, and if the buyer is ignorant about the pricing, and then the seller can take high price from it.
Yeah. So in this case, we assume that
the buyer is very vigilant. Then, and if buyer is done all survey of the competition, then seller cannot expect high price.
no. So here in this case, what we the assumptions are that the buyer knows his valuation very well, and the seller knows the distribution very well. You can actually argue that both of these are unreasonable. Yeah. So what you have argued is that the buyer may not know his valuation very well. The other argument is that the seller may not know this distribution very well. So how does he? Yeah, I mean, so we are modeling that the distribution is somehow known, right?
It's a perfect setting in which you are assuming that buyer is fully aware
of his valuation, and the seller is fully aware of of the distribution of the buyer. So and I mean, this is all Meyerson's result. So I have not come to my results as yet. Yeah. So and I mean, this is a complete result. So in this setup, if you consider one item, okay, I mean, this is a very nice setting, and there is a very nice answer as well. So the issues come when we actually go to the two item setting. That's where I'm coming to. Okay. All right. So yeah. So the point that I was making is when there is uniform distribution, I think we are convinced why the reserve price has to be half. Okay. Now consider the next distribution. where you have 2 into 1 minus x. Okay. So, I mean, you can see that in the second example.
But here, these are the ideal cases, no?
Yes, yes, yes.
These are the ideal cases. Otherwise, if I want that nobody should be in the competition, I offer a very low price. I is bound to say.
No, so here there is only one seller and one buyer.
Only
So,
one seller and one buyer,
yeah.
and I want to buy it anyway.
No,
so
so
that-
what if I quote them 1 crore rupees? You
Okay.
will never buy it for sure. So, I mean, you have some thresholds and all that. You have a budget, and yeah, so these are modeled as knowledge of distribution, for
So
example.
these are the normal cases.
Yes, yes, yes.
You can make the case more complicated.
Yeah. So, I mean, in this case, why I am describing this is because I want to let you know that one item setting is of this sort. So, in this simple setting, you go to 2 item settings, there are much.
So
Hardness.
you are just taking slowly. You are going.
Yes. And not in the direction that you have mentioned, but instead of 1 items, you consider 2 items. In the same setting, the problem becomes difficult. Yes.
The picture which you are talking about, what is that? Sellers, the knowledge of the distribution the seller has, what is that? Can you explain?
So, I mean, as I said, so suppose, I mean, the seller knows that if it is between 10 rupees and 20 rupees, you will buy it. Okay. I mean, it could be uniform, for example, or it could be, for example, of this sort, right? So, where it is, I mean, what does 2 into 1 minus x mean? It means that, the chance of him buying is very high when it is low, and it tapers down when it is high, right? Yeah.
How is the data point?
Okay, so can we-
How can
when
seller
we
know
postpone
that range
questions
is
to
10 to 20?
What is
the question?
How will the seller know this data that it is between 10 to 20?
so that is not the point of the discussion. I mean, so the problem assumes that it is known.
Okay, can we postpone those questions to the end because the speaker cannot proceed? So let's return to the.
Okay. All right. Yeah. So yeah, in the second case, for example, as you can see, the buyer is you can say more stingy, for example, right? So in the sense he is more ready to buy when the price is low and not so much when the price is high. So you would possibly expect a lower reserve price in this case, and as you can see, if you compute P, in this case it turns out to be 1/3. Okay. And similarly, on the other direction, right? So one who is, ready to spend more money. Okay, when f of x is 2x, right? You can see that the reserve price is 1/√3, which is more than 0.5. Okay, fine. So I think we took a lot of time in one item setting. Let's go to the 2 item setting. Okay, so consider the same problem, but instead of 1 item, you have 2 items. There is only one shopkeeper and one buyer, but let's say there are two items to sell. Okay, let's say a pen and a pencil, for example. Okay, so what should be the answer? I mean, one would immediately guess that, an immediate guess is possibly that perform Myerson auction separately for each item, right? So take a pen, perform Myerson auction, take a pencil, perform Myerson auction again, right? So would that not work? Let's see. So suppose consider this example, Z1 and Z2, where it is uniform with 1 and 2. So this is discrete. Okay, so that is 1 with probability half and 2 with probability half. Okay, so in that case, I mean, one can find that the reserve price is 1. Okay, so both the items are sold for 1 rupee and the auctioneer gets 2 rupees, right? Instead, I'll give you a slightly different auction where, so now you have 4 possibilities, right? So you have 2 items. Each of the item can have 1 or 2, right? So it can be 1, 1, 1, 1, 2, 2, 1, 2, 2. Of which, if it is 1, 1, I'm not selling it. Okay. For the other 3, I am selling both the items for a price of 3 rupees. Okay. In that case, my average revenue is 3 into 3 by 4, which is 2.25, which is more than 2. Okay. So by using Myerson's auction separately, I am actually getting a suboptimal answer, right? So I have a better example. This turns out to be the optimal answer. Okay. So what this means is that if I bundle the items together instead of selling it separately, at least in this example, I'm getting a higher revenue, right? Okay. So maybe our intuition was just wrong. How about bundling the items together and then performing Myerson's auction on that? Maybe that is that a better option? So this example says that's not the case. So for example, let's say for the first item, your valuation is 1 with probability half and 2 with probability half. Similarly, for the second item, it's 1 with probability half and 3 with probability half. Okay. Again, you have only 4 possibilities, right? Of which in 1, 1 you don't sell it. Okay. So this is Q1, Q2, T. Okay. So it is, you don't sell it at all. When it is 2, 1, you sell the first item with probability 1, second item with probability half, and you charge him 2.5. Okay. For the other two, you sell both the items with 1, 1, and the amount you ask him to pay is 4 rupees. Okay. So this turns out to be the optimal option. Okay. So what this, I have 5 minutes. Okay. All right. So I can't do much. So yeah, what this tells us is that the allocations are no more deterministic. So yeah, possibly to come to this point, I had to spend a lot of time. So recall that in one item setting, whatever the distribution was, okay, you can scribble any distribution, and if you find the optimal auction, it turned out to be deterministic. In fact, it was take it or leave it offer, right? But here I have taken a very, very simple example. It is a discrete example with just the support set having only 2 elements, right? And here the optimal auction is no more deterministic. Okay. So what is actually the right answer? How do you compute the optimal mechanism for a general distribution, right? So recall that the problem for one item was solved in 1981, but the problem for 2 items is unsolved even today. Okay. So yeah, of course, solutions for certain distributions are known. So this is one interesting distribution. So I'll mention this and then move to at least some of our results. Okay. So suppose consider this continuous distribution where the first item is uniform in 0B1 and second item is uniform in 0B2. Okay. So what is the optimal auction? So the buyer sells the first item for a price of 2B1 by 3. The second item for a price of 2B2 by 3. But if he wants both the items, he need not pay 2B1 by 3 plus 2B2 by 3, but he needs to pay something small. Okay. So it is like saying that I'll sell you the pen for 10 rupees. I'll sell you the pencil for 5 rupees. But if you want both, you don't need to pay me 15, pay me 12. Okay. If he does that, I mean, he gets a higher expected revenue. Okay. So what this means is that at least in this example, an interplay of individual sale and a bundle sale actually helps. Okay. So yeah, there are a few distributions for which the answers are already known. Okay. Like beta distributions, uniform distribution, exponential distribution, and so on. Okay. But all of them were known only when the support sets were of the form 0B1 cross 0B2. Okay. So if it is in a different region, let's say C1 plus B1 cross C2 plus B2, say 10, 20 and 20, 30 or something of that sort. So these methods did not work. Okay. So that's where we step in, I can say. Okay. So there are many things I wanted to describe, but due to the lack of time, I'll just describe my results for uniform distributions. Okay. So basically the work is analyzing the optimal mechanism for distributions where the support set is arbitrary rectangles. Okay, not just 0B1 cross 0B2. So let's say, for example, it's C1 plus B1 cross C2 plus B2. So it's an arbitrary rectangle. Okay, not just those bordered by the coordinate axis. Okay. So in fact, our analysis is how the optimal mechanism varies when the support set is shifted in scale. Okay. So yeah, let's go ahead because I'm just going to consider the special case of uniform distributions. Okay. So we saw that the answer for uniform 0b1 cross 0b2 is the interplay between individual sale and bundling sale. Okay. So if you shift and scale the rectangle, you also expect the mechanism to shift and scale in some sense. Okay. Unfortunately, that was not the case. What we got was that based on the values of the C1, C2, B1, and B2, we got these 8 possible structures. And I mean, one of this could be the answer based on the values of C1, C2, B1, and B2. Okay. So to explain how notoriously hard this problem was, so I started working on this problem in 2014 during my PhD thesis. Okay. And by completing this, I actually got my PhD. Okay. So I mean, that just to say how hard this problem was. Okay. So yeah, I'll just spend a minute on these structures. So what is the reason for having so many structures? I mean, so how does uniform 0b1 cross 0b2 is very different from uniform C1 plus b1 cross c2 C1 plus b2. Okay. So let us actually observe the structure for just these examples. Okay. So for example, yeah, so for this, we have just seen the interplay. Okay. Suppose I move the rectangle here. Let's say it is 100, 101 cross 01. Okay. So it turns out to be that the individual sale is the optimal mechanism, or even here, the individual sale is the optimal mechanism. And if you move in this direction, say 100, 101 cross 100, 101, so bundling turns out to be the optimal mechanism. Okay. So yeah, now let's answer why so many structures. So the values of C1 and C2 actually represent the guarantee amount from the buyer, right? So what does it mean when you say that the distribution is between 100 and 101? That means that the buyer is actually guaranteeing that he's paying 100 rupees, right? So that's a huge information to the seller. So what if the distribution is uniform, right? So why should the seller behave in the same way for 0, 1 and 100, 101, right? So that's very different, right? So that actually tells why, I mean, the various values of C1, C2 actually gives a very different answer, and that's what our work had to do on optimal dominance. Thank you.
Thank you very much.
Thanks.
Souvenir from the organizers.
Thank you.
1 minute.
He's taking from this.
End of comment session.
What's next? No, not few.
So, how long you been working on this?
Next, we warmly welcome Dr. Leonard Justin, Assistant Professor from the University of Twente, Netherlands. Dr. Justin is an expert in economics and game theory,
Thanks for the tip.
including stochastic, cooperative, and evolutionary games. His research interest also covers areas like industrial organization and development economics. He serves as an advisory editor for the Journal of Evolutionary Economics and has played as a key role in academics mentoring, having guided over 120 master's and 39 bachelor's theses. He also been part of the scientific program review for major Dutch research initiatives such as the VD program and the program on evolution and behavior. Over to you, sir.
Thank you.
So the next presentation is a video presentation. The only thing I have to worry about now is communicating to the speaker that maybe time is up or time is limited. The next speaker is Dr. Dietrich von Rosen. He holds a PhD from Stockholm University and has made multiple contributions to multivariate analysis, probability and statistics, and regression analysis. He has been actively involved with currents, playing a significant role in its research and academic activities. Dr. von Rosen has supervised numerous theses across all levels and has published over 120 journal articles and 3 books. He also serves as the editor-in-chief of the Journal of Multivariate Analysis. He is an honorary doctor of Tartu University in Estonia and a guest professor in Beijing, and has delivered invited talks across the globe, including India. We're honored to have him with us today. The floor is yours, sir.
Yes, thank you very much. We should do these technical things now. And I cannot share here anything. Oh, yeah, hello. Do you hear me?
Yeah.
Okay, good. But I cannot share my screen here.
You want to see your
Yeah.
slide from here or you like?
Yeah, no, wait, now it came. We should see if it's...
We have allowed, sir. Just check. Yeah.
Do you see it now?
Yes, we can see.
Because it was some time ago I used this Zoom, but we should see.
Yeah.
If it doesn't work, you have to interrupt me or stop me. And as far as I understand, I have around 40 minutes for a presentation. And yeah, first of all, let's start. So thank you very much to invite me to this meeting. I'm very happy. I'm a bit unhappy that I cannot join you on place, but I will come to in December to Manipal, at least. But this time I couldn't do it. As far as I understand, there are pretty many non-statisticians here, and I'm pretty conservative, traditional mathematics statistician. So, and looking upon, how to say, inferential part, not the probabilistic part of the subject. So I will try to guide you a bit through, what to say, classification analysis. Also in textbook, you usually connect the discrimination and classification, but I think today it's more or less only about classification. And I will talk a little bit about the growth curves are just here to illustrate the problems, but I have to mention a bit more about the growth curve model, I guess, and which I don't have slides, but I will try to present it. So the title is Classification of Growth Curves when Unknown Population Exists. And I will soon try to explain what it is. If we look at classical, say, discrimination, classification, it has a long history. And in fact, the history, in my view, starts in India. And it starts a very long time ago. Key persons, I think, it's about, Carl Pearson, Mahalanobis, of course, and then Fisher. And then there are some other persons around it, but I would say the essential person is Mahalanobis, in fact. So, about 100 years ago, a bit more, Carl Pearson wanted to classify bonds. And in some way, this is one of the original subjects to classify bonds. Even though in India, there was an interest to see to which, say, tribe bones, they found bones in soil, and they wanted to see if they came from the same population or there were different populations involved. So this was an important issue more than 100 years ago. But Carl Pearson, they talk about Races, what we don't do so much today, or we should not do it, but it was pretty hot topic, I would say, in the beginning, or 100 years ago. So Pearson introduced something like called coefficient of racial likeness, CRL. And there was one problem with it, and this was in some way discovered by Mahalanobis or other people also, that it was like it was not really a test of hypothesis, but the coefficient depended on the number of observations. So the idea then, and which at least Mahalanobis was successful with, was to create a distance between population, which was independent of the number of observations. And this has created this Mahalanobis distance, which so many are using today. There is another, Mahalanobis is interesting for many, and there's a nice review of his contribution by Dasgupta. But as far as I understand, Mahalanobis was inspired by a huge conference in London, and in particular, it was on races. I don't know, it was something connected to research about races. And the books are available, the proceedings are available on internet, and it's interesting to see how one was thinking and discussing. And Mahalanobis became inspired by a person, Seal, and this was already 1911, when one discussed distances between groups, and you had variables as coordinates. So in some way, this is a very early contribution to multivariate analysis. I think Seal was also from India, in fact. Okay, but then later, another way to discriminate between population is to make formal testing. And multivariate testing was in principle laid down by Hotelling and around 1930, or the first paper I think is 31. And then later ideas from that paper and other, it was taken over by Fisher, and Fisher contributed by himself. And he has I think he usually called Fisher to be the father of discriminant analysis. And this was a work, his work was published 36, but they had some kind of collaboration with people before, where they in particular looked at growth curves also, and discrimination between populations. And this was some year before 36 it was published. So what is the problem here? We can generalize it, or very simple tell you about it if you look at this figure. So what we have here are repeated measurements on individuals from two populations, pi 1 and pi 2. And the idea is then you have a new observation, X, which also consists of repeated measurements. And all of these, today we look at balanced data, so everyone is measured at the same time points. So we should decide now if this new observation X belongs to population 1 or population 2, or it doesn't fit. So this is a basic idea, and it looks simple, and in particular, since and a lot of classification is going on, and if you look into the modern view of and AI or whatever, one branch is of course classification. But the issue I want to stress today is that maybe this new observation X doesn't have to belong to either of these populations. And then you can see that very little has been done in this direction. So we can, I would say, this Barnard was collaborated with Fisher, and they did like classification of regression lines. But then what I want to stress is CRO in an overview talk in England, UK, 48, he gave a hint about this classification, what he called into an unknown population. And it means that you cannot classify it in population 1 or population 2. So this is an old idea, and it has not really been, you don't see it in textbook, how to handle it. So there are not so many, what should I say, basic contribution to it. And today I will talk about the growth curve model a bit. And this is a Potthoff and Roy model from 64. And there in that model, I will try to explain it also. I don't have slides with me later. But it was from end of 50s, Rao discussed growth curves. And the problem with growth curves is that you have repeated measurements which are correlated. And since they're correlated, you have a covariance matrix. And usually that covariance matrix is supposed to be unknown. So then you want to estimate. You want to estimate the mean parameters. You want to estimate the covariance parameters. And this is pretty tricky in some way. And I will try to explain why. A good solution, or the paper who solved the maximum, found the maximum likelihood estimators in the growth curve model was by Khatri, and it's 66. And this is, there are interesting ideas in these papers. If you think about classification of growth curve, one has to mention one paper, and this is by Burnaby. I think you pronounce it Burnaby, 66. It's early. It's almost at the same time as Khatri solved the maximum likelihood problem for the growth curve. And but the approach by Burnaby was a bit different when classifying. He thought this growth was a nuisance parameter, a nuisance effect. So he wanted to get rid of it. And he did it in a certain way. And later turned out, I learned to know it doesn't stand, but you can see it in some of these CRO's paper, that in fact CRO was involved in this paper also. So this is a pretty brilliant paper with nice interesting by Burnaby. Later there have been works, discrimination on growth curves. And I can mention this Shirsagar and Davis, but it's more about testing hypotheses. And so there are some people who have been working with it, but it's not very frequently. And there's a Bayesian literature also with Jack Lee from 82, discusses classification of growth curves. And if you just want to know about and classification, then there's a pretty big volume of book by McLachlan. It came in the beginning of 1990 now. It's a second edition, 2004. And there you can find very much about discrimination and classification. There is a small part about growth curves, not much. But still, the book is definitely of value to look into. If you want to have more classical work on the growth curve, classical work means that you are interested in not just classification, but also the errors of misclassification, which is a tricky part, in fact. And then I would refer to books by Srivastava and Khatri, Muirhead, or T.W. Anderson's volume. And then you can, where you see what is required in order to find an approximate probability for the misclassification error. And today I'm not going to talk about the misclassification error. It's just about finding a classifier. And if you look a bit into what's going on today, we have data mining, artificial intelligence, but in many of those contributions, it's a bit different than statistics. In statistics, or at least my philosophy, is that we should have some kind of theoretical population. And so everything in statistics is about models and we discuss the models and we discuss properties of the models, and that includes estimation of parameters. Whereas when look in the more newer literature on data mining, machine learning, and what you can call it, it's more about the data itself. But the data from a theoretical point of view, in my view, has very little information. But for certain, one has to think when to use it and when not to use it. So I still believe that models is the proper way often to transmit knowledge to the next generation. Data hasn't that strength. Okay, now we come to some kind of technical background. And I should have talked more about the growth curve model. And unfortunately, I don't have a pointer here. But if you look at the first equation here, x1 partition with a small x, which is going to be classified. And then you have a model here equal A. The model is A times beta 1, and then a 1 vector, the transpose of it. And then we have an error matrix. In some way, that describes the growth curve model. And A is a known within an individual's regression or design matrix. It means with this A, you model the structure over time. So if you have a linear growth over time, A will consist of 2 columns. X1 and X, they also, here we call them, they have size P, the columns in that matrix. And then you have N or N1 plus 1 independent columns. Now we took N1 because it's from the first population. And beta 1 here is an unknown parameter. I mean, usually we will call later B to be an unknown parameters. The one vector is just that all elements have the same distribution. Usually, if you want to generalize it a bit, it's no difficult at all. You just can have an arbitrary design matrix, so-called between individuals design matrix. And then you are, if the A matrix would be the identity, you would have a MANOVA model. But anyhow, this beta 1 is unknown. If you look at the error matrix, it's a multivariate normal. We need to assume normality here. I can explain later if you want. And then it consists of the matrix normal distribution. It has a mean 0. And then there stands a covariance matrix sigma. Sigma is unknown. And this is all variances and covariance within each column. It's described by sigma. And that sigma should be estimated. And since we have N1 plus 1 independent observation, the last parameter in this matrix normal is identity N1 plus 1. And we can mention this model, usually linear models, belongs to the exponential family. But here the growth curve model doesn't belong to the exponential family. Yes, this A matrix shows that it doesn't belong to the exponential family. It belongs to the curved exponential family. And there's a big difference. And you will see on estimators, which I'm presenting. So, okay. Now back to our classification problem. You have your observed or the the X which you want to classify, and I don't distinguish between observations and random variables now. This is tradition, but it's not always so good. So I have my X here, and if I assume it to belong to population 1, I have the first scenario, the first two equations. So I have for the first population this A beta 1 and with n1 plus 1 observation, and then I have x2. Are the observations or the random variables corresponding to observation of population 2. And then I have the opposite also. I can, if x would belong to population 2, I will get the 2 equation on the bottom of the slide. We can put them together here side by side. They're a bit messy details, but I will not say so much. It's that we have a defined new design matrix which consists C1 and C2, which depend on which population or which scenario you have. If X belongs to population 1, we have C1. If X belongs to population 2, we have C2. And the X matrix will always be the same, that we have a partition matrix with all the observations included. And then we have sums of squares matrix, S and S tilde or under tilde, which is the usual sums of squares matrix in multivariate analysis. And then we can see, I will not tell you how the estimate of the mean is, but the maximum likelihood estimate of sigma, when we have C1, that means when X belongs to population 1, it looks like this, and it's the total number of observations is n, is n1 plus n2. So n plus 1, this estimate of sigma, and then we have a sums of squares matrix S, and then we have another object where you see a bit that we have in fact a projection here that A transpose S inverse AA transpose S inverse, but this is random. Since S is a random matrix, then this is also random. So it's pretty complicated, and it's in some way pretty fascinating that one is able to find explicit estimators. And this is unique, that estimator. And then we have also something in the middle that X, also a quadratic form in X. And this is a maximum likelihood estimator sigma. And this means that it's the distribution of this sigma is difficult to derive. One can do it, but it's difficult. You can also see, if you would look as a usual MANOVA situation, not the growth curve situation, but the MANOVA situation where this A equals identity, then you will see that the second term here disappears because the projection on the orthogonal projection on the whole space is 0. So, and we have the same estimator of sigma under the alternative. It's given in the bottom of the slide. So when X belongs to population 2, it's given there. And then the idea here is, of course, with likelihood classification, that you form the likelihood and look at the ratio there. So the ratio is given here by lambda. I have, of course, there's some coefficients in like minus n half in the of the determinant. This is not. We can just don't have to consider it. So we have the decision or the classifier here will depend on the ratio of these two determinants, which have a complicated distribution. And then you can see how we have the projection on top that P of A and S is given as usually orthogonal projection on something where the inner product is defined through S. But anyhow, the determinant is important, and we can start to manipulate it, and I will not show you details about it. What is more important at the second expression on the slide for lambda, that at the end you have S divided by S tilde, and then you have this AO transpose S AO inverse, AO transpose S tilde AO inverse. That is an important quantity, and AO is any matrix which generates orthogonal complement to the column space of A. So if A is a full rank, this would be 0, then this would not work anymore. But now we suppose that the A is not a full rank, and then we have these 4 matrices here in lambda, which we should consider. So first we consider this the determinant of S and S tilde. And then you manipulate, and an important quantity is this on the which you see in mid of this slide, S1.2 or comma 2, because S1 comma 2 is independent of the observation which is to be classified. So it is true if X belongs to pi 1 or X belongs to pi 2. And we will know also that this S1 comma 2 is Wishart distributed. But here we just go on to manipulate, and we can manipulate pretty much, it's pretty straightforward calculations. And you can see at the end of this ratio here in the bottom of the slide that the ratio between S and S tilde, or the determinants of it, it's a function, it's a ratio which includes the average x1 is the average of all individuals, and the same x2, and then you compare the new the observation x which you want to classify. So you look at the difference between this is the average of x1 and the new, or the observation which is to be classified. And you see this is the sum of Mahalanobis distance. It's a ratio between 2 Mahalanobis distances. So this gives some idea that this S, the determinant S and the determinant S tilde makes sense to study. The same with the second ratio. One can manipulate it a bit, and I think I will not talk too much about it, but you can see that in the bottom of the slide, you have an expression which involves this A matrix, or A. And in fact, this is some kind, you can look upon it as a square of an idempotent matrix or projection. So there you project observations on the column space of A. So you first have something which is belongs the difference between X and the average people, or average and individuals in the population, and then between X and the average population, but you project it on the structure on A also. Now I give you in some way the result, and then we give some examples, and then I have a feeling that soon I have to stop here. But and the likely ratio, which is very interesting, it can be written as the ratio of 2 determinants. And that ratio can be and it can be manipulated a little bit more, and we want to do there in some way 2 aspects here of it, and we should see it can be manipulated also, like we have L1 and L2, and they are given below, and that should be smaller or equal to the right side, which we also have discussed. And as you can remember, it was a determinant of S and S tilde. And then we have this L1 and L2. So in fact, we can see that there is a difference between L1 and L2, which are of interest, but also on the right-hand side, that difference is also of interest. And if we start to check if there's a difference between, or where to classify this X, where it's largest on the right side, we should take that into account when comparing L1 and L2. So if you look at L1 and L2, then you can see at the bottom here also that you have the mean structure, and then you project the observation on that on the column space of A. And this is and then you have an inner product, estimated inner product, which doesn't depend on X. So this there is a clear interpretation here also what the ratio of L1 and L2 do. If X is closer to population 1, then of course L1 should be smaller than L2. So all this discussion end up in a proposition. So we want to classify, or we're going to classify, and we, as I mentioned, we have two criteria. Suppose that the criteria one was in some way, it was about the ratio of determinant of S and S tilde, and that is reformulated in as it stands on the statement 1. So this is one criteria. And then we have another criteria, and statement 2, which is about the structure of the growth curves, where we project the observations on the growth curves. And remember, this is everything is in some way about likelihood here. It's not ad hoc. We want to see where the likelihood will be as small as possible, or that will drive our classification rule. And what is special with the statement 2 here is that there is this constant CO, which in some way depends on what happens in 1. So we should not say that the L1 is smaller than L2, but we should also take into account the CO. That makes the classification pretty fair. So then the rule is that we classify observation X into population 1 if both 1 and 2 are satisfied, and we classify the observation X is no one, or if not 1 or 2 are satisfied. And if statement 1 goes in one direction and statement 2 goes in another direction, then we say that X is classified as belonging to an unknown population, which is equivalent to say that the X doesn't fit to any of the populations, or either population 1 or population 2. So this is some kind of basic ideas which we have, and I will finish here with some examples. So the first situation, you have two populations and you have your new observation here, and it seems there, it seems pretty likely that X should be classified to pi 1. And then we have second, the B, in the B figure here, you see that X is pretty close to pi 1, but it differs in the slope. The slope is exactly the same as pi 2. And then we have to think how we should classify such an observation. And it seems that our criteria can work to handle it. We have other things here also. Here we see in C that we have an observation which, if we should classify, it should be classified in population 2, but it's pretty far away. So is it so far away that it doesn't make sense to, or one should not classify it in population 2, even if the slopes are parallel? And then we have a case D here, which is pretty obvious that it doesn't work. So I will not, should there are more technical things here, we forget them. And what I'm doing there is in some, I add some more classification criteria, 4 more. And it has to do with that we have more than 2 parameters in our model. So if we have 2 parameters in a model, then it can be so that for one parameter, we can classify, say they have the same intercept, but the slope is different. And then we cannot classify, and vice versa. and we can do something more with orthogonal complements. So we come up in total of six rules. So if we go back to here to our cases or something similar to in ABCA, it's the observation belongs to population 2, X belongs to maybe to population 2 and B, and in C it deviates pretty much from population 2, and in D it belongs to population 1. If we look at this criteria now, from 1 to 6 here, if you look at the case A, we see that all of them are positive, and it means that we can classify our X into population 2. If we look at the B, then you see the criteria 1 and criteria 2 is those we have discussed before. And here the criteria 3 to 6 are these new additional criteria. And then you can see that one of them deviates. It's not the same, it goes in another direction. So then in some way we should not classify X into population 2 here. And even it's more pronounced here that in the population, the T we have two criteria 3 and 6, which are negative, whereas the others are positive, and we should not classify X anywhere. And then we have the last case here where X belongs to population 1, and then we see that all criteria are negative. So this works pretty okay, but of course in reality, if we have many parameters and more complicated models, we cannot have so many. Just for this linear regression or linear with repeated measurement, 6 criteria is almost too much. So one needs to have some kind of strategy and needs maybe to be pretty humble if one of many criteria are negative or positive, that they deviate. So there is the statistical experience will matter. Okay, this is my last slide. Thank you very much for listening and inviting me to this session.
Great. Okay, word. Great. Now it works. Thank you for this presentation. Are there any questions? No questions, sir. So I think everything was extremely clear. And thank you.
I don't think so.
Well, it's for me, it's difficult to see what is your cutoff point. You have to have 6 criteria, and then in this case, and sometimes all of them are positive, and that's good news in order to classify. But what do you do when 2 are, as in the example, when 2 are negative and 4 are positive? What do you do? Where is that? Where is the cutoff point? What do you do?
No, this in a strict sense, and we haven't discussed it so much. In a strict sense, I would say I classify that observation to an unknown population. But I can admit that if if you would increase with a bit more parameters, that you would have 20 criteria, that some is negative and whatever, it can very well be by random.
So that's two negative.
But I don't know today. That's because we don't have any distributions on this here.
Okay. That's an open question.
Yeah, but otherwise the criteria here is less or equal to 0. No, less than 0 or larger than 0.
Yeah.
This is how we are seeing it. This is a cutoff now, but this is because we don't use distributions here.
Okay, thank you. So let's give a hand to Professor Rosen.
Thank you. Thank you, sir. Thank you for chairing the session. Now we have come to the end of the first half of the first day. So we have 2 o'clock is the inauguration session starts here. 2:10 we have to actually be here, so we can start by 2:15. I'm sorry. So 2 o'clock you have to come here. That's what I mean. So that's why we have actually winded up the session a little bit early. So we requested the previous session speakers to actually reduce their talks by 5 minutes to accommodate lunch hour extra. So please come before time so that we can start the inauguration time online. So our admin people and other people will be there on time. So we wanted the participants also to be on time. Okay. Thank you. The buses are actually already ready down. We'll have the lunch over there where we had our breakfast, and then we'll be back from there itself by picking up by the same bus and then come over here. Anybody wish to walk, you are free to walk, obviously. Thank you.
That place is far off.
You can also in the short days or short kill. Back you can keep it. You can leave your materials here. We'll make sure that the doors are locked. No problem. You just carry your most valuable things, at least, just in case. You have exactly 1 minute.
1 minute.
Yeah.
It's not raining.
No.
Scared of the rain. Doesn't?
That was not needed.
It's not.
Yeah.
You don't have rain there, Roland? We don't have such rain. Sometimes it's raining and we just don't care. Okay, can I water?
You would care for the monsoon. That's really something.
There is water there? Yes.
You take food and come back. Really like. No.
I'm going to
we came to know certain things, no, that he can interpretation we came to know from him. So we really benefited, and those who are at ISI that time, no, that all of us benefited. And then that further that he wanted to hold that one Guru Pulam, no? So that started with so there are that Janofles, and so like that there are many to whom he has collaborated, and in fact that when we organized this conference, when we wrote to many people, know that everybody reacted, but those people have also become old, no, that so when he approached to Frank Teichmann, so he is already that he is in that just now that I got the information that he is in hospital, right? He is in hospital and he could not come here. No? That, who was that contemporary of that to whom Raghavan used to work? No, Pastor Raghavan used to work. But we made a lot of effort, no, that to bring all of them together, and the effort started, no, that also that to dedicate some special issues, dedicate to both of them. We spent T. Patrasarthi and T. S. Raghavan, and 4 issues, no, that there are never that so many issues, for special issues, and we got help from our from the committee members that. It was Martinez Ligas and was Lena Melogy. So like that, we have got help from them, and we could get 3 to 4 special issues. And I hope that those who are here know that if somebody has done something based on the Raghavan's work, for example, that ARA stochastic games with ARA structure. So it was his ideas. If anybody has worked any of the topic of the stochastic games, or even even the static games, any topics of static games or dynamic games or semi-Markov games. So I will be happy to do it. I mean, in his journal. So there are the special issue dedicated journals, International Game Theory Review or optimization or some other journal. That we will be happy to take it. Of course, that papers will be subjected to usual referring, that is the journal procedure. It will not be accepted as it is. It will go through the journal procedure. But I hope that that all the invited speakers, those who are here, they will make their effort to give their this one, no, dedicate one of the paper to in the name of Professor Raghavan. Okay, and so with these few words, that I again thank Professor Raghavan, from whom I have learned a lot, and hoping that since his pair, that Sati Parthasati who used to say that they are the pairs, so that they used to talk each other, fight with each other. No? But when he passed, no, then he just completely became silent. No? So nothing he talks about him. So they are so much attached, and so now in fact T. Parthasarthi was a that we are neighbors, and he was a good this one friend of us, the co-worker. We have written several papers together. So I really miss him, and of course now Professor Raghavan is 85 years. So he would have come here. Many of are asking that whether he can come here or not. But 85 years coming from US is very difficult one. He'll join online. With these few words, thank you.
Thank you, Professor Yogi, for sharing your experiences with T.S. Raghavan and also his contributions to the mathematical sciences. We are honored to have Professor Juan Legas with us as chief guest for this event. So I'll introduce you for some time. 2 minutes. So, Professor Legas received his PhD in applied mathematics from the University of Barcelona in 1981. He is a renowned scholar in the field of optimization theory, convex analysis, generalized convexity, and mathematical economics. He has made significant contributions to both theoretical research and academic leadership. Since 2006, he has served as the editor-in-chief of the journal Optimization and is a member of the editorial boards of several prestigious journals, including the Journal of Convex Analysis, Journal of Global Optimization, TOP, and Set Valued and Variational Analysis, among many other journals. He has also served as chairman of the Working Group on Generalized Convexity from 2000 to 2002 and has been associated with MOVE since its founding in 2009. Professor Legas' distinguished academic and editorial work continues to shape the global research landscape in optimization and mathematical economics. We are sure to realize his passion for academics and research with his inaugural address. Sir, now over to you. You can address the guest.
Thank you very much for your kind introduction, which I was about to miss because of my impatience to talk. So it would have been a pity to miss your kind words. Thank you very much. Well, dear authorities, dear colleagues, ladies and gentlemen, it's my pleasure to be here. And I think I can speak in the name of all the participants to thank the organizers to arrange the conference. There is a very interesting program with many interesting talks. For me, it's always a pleasure to come to India for many reasons. I may have developed some addiction to come to India, but I'm not alone. I'm seeing 2 other European participants here whom I never have met in Europe. I always met them in India, but I think they are European in reality. And this is, I think there are good reasons for that. I mean, coming to India for me means a lot from many points of view. First of all, India in itself is a very fascinating country. As it is perceived from Europe, it has the most ancient culture in the world, which is still alive. I try to avoid the word old. I prefer to say ancient, because the word old has a connotation that maybe it's about to die. And it's not the case, of course. It's full of vitality. And I think one of the reasons for this is that the Indian culture is very diverse. And the diversity brings vitality. And so it's very nice to see to have manifestations of the Indian culture when one comes here. On top of that, if you have wonderful landscapes, wonderful monuments which are unique in the world, and wonderful people who are also unique in the world, then you will understand the reasons for our addiction. In my case, I have also to add that I have excellent friends in India, in Kanpur, in Varanasi. They are my good friends, but I am not their good friends. Why not? Because at this moment, I have a visitor in Barcelona from BHU, and I left him alone to come here. So I'm not a good host, as you can see, but okay, he is going to stay there for 4 months, and I come here just for a week. in fact, I canceled other conferences just to be with him. And from a mathematical point of view, it's very interesting to come here because there is a lot of interesting mathematical activity, in particular in our fields: operation research, game theory, optimization. And it's a unique opportunity to get in touch with the Indian mathematician to see the work that is being done here. And it's particularly very nice to see that many young people are appearing every new year with new research, new presentations at conferences, etc. So I was talking about the vitality of the Indian culture, and to this I can add now the vitality of the Indian mathematics, at least in our field. So it's a real pleasure to be here. I think, I'm not sure, but I think it's my 10th trip to India. And second one this year, but not the last one this year. I'm going to come twice more, once in August and another in October. Somebody said something like I can resist everything except temptation. Well, I joined this sentence. So whenever Professor Nyogi, who keeps inviting me repeatedly to go to the ISI India to Delhi for a conference, I can never say no. I mean, no matter how busy I am, I can never say no. And the same to come here. So it's very nice to be here. So I welcome all of you. I hope you all will enjoy the conference as I'm enjoying and going to enjoy it. Thank you very much.
Thank you, Professor Ligas, for sharing your connect with India and your interest to be here every time. Thank you, Prof. We have with us our very own director, Professor Cherian Varghese, as the guest of honor. Professor Varghese assumed his role as director of PSPH since July 2024. Prior to joining MAHE, he had a distinguished career spanning over 2 decades at the World Health Organization, WHO. At MAHE, he now leads PSPH's academic research and global engagement efforts with a vision to strengthen public health education and evidence-based policy making. Dr. Varghese is the recipient of numerous honors, including the WHO Regional Directors Award of Excellence 2023 and the Norman Campbell Excellence Award in 2019. I kindly request Professor Cherian to address this gathering. Over to you, sir.
Thank you, Ashma. Good afternoon, everyone. Manjunath Prasad should be congratulated first for his steadfast commitment towards making this happen. Professor Samir Nyogi, SAC chairperson. Professor Juan Enrique Martinez Legas, muchas gracias. That is the Spanish that I know of. Dr. Narayan Sabahit, our Pro-Vice Chancellor, and Arun, my colleague, and all the friends and participants, international participants as well as national participants. I come from the field of public health. In fact, I started as a medical doctor and then went into epidemiology and then ended up in global health. So 20-30 years back, if you study statistics, that is the only thing that you do. Or you do public health, that is the only thing that you do. But the things have changed now. I think it has to be really an amalgamation of things to make things happen. So if you take I was in the morning in giving lectures on a course on non-communicable diseases, which is currently the major public health problem, like heart disease, diabetes, cancer, and all that. One of the determinant is air pollution. How do you understand air pollution? How do you actually quantify that? How do you optimize what is the risk? And how do you make into decisions? We need your brains for that. We were looking at commercial determinants. You know, most of the things that we eat or drink are basically because of commercial activities. So how do you understand commercial activities, which actually gives to unhealthy products like unhealthy foods and all that? So in every aspect you look at, you either need good LLM to understand what is going on, or you need good statistical models and to understand how to sort of optimize resources. you heard that I was in WHO. WHO, as you know, is in big disarray with Trump pulling out. So with very minimal resources, how do you understand global health? What can we do? How can countries optimize the minimal resources to manage the multiple problems that they deal with? So I think in every area that I can think of, I think optimization, gamification is another very important thing to actually help people to live healthy. There are a lot of healthy living apps where actually gamification comes in. So I think in every area that we need to think of, we need to see how the brains that is in this room can actually contribute to public health and global health outcomes. So I'm very pleased to see that this is happening. The School of Public Health is very unique. We have School of Public Health with public health as a core business, social work, hospital administration, but one of our big departments is the Department of Applied Statistics and Data Science, which is actually organizing this. So I think that sort of coming together is what I would really think should happen in multiple institutions so that we can come up with more concrete solutions with minimum resources that we have. With that, thank you very much for coming for this meeting, and I hope success for all of you and look forward to good outcomes from this. Thank you very much.
Thank you, sir. Thank you for your insights into the applied mathematical sciences. And now, the souvenir of Icords 2025 is all set for its release. I request the dignitaries on the dais to unwrap the souvenir and mark its release. Thank you. Thank you, everyone. Our dear Pro Vice Chancellor Technology, Professor Sabahit, is a distinguished academician and an administrator with over 34 years of experience in teaching, research, and institutional leadership. He holds a PhD in geotechnical engineering from IIT Kanpur and has served in various pivotal roles at MAHE, including head of department, director of MIT, director of admissions, and as well as registrar. His significant contributions to curriculum development, quality assurance, and institutional accreditation have been instrumental in the growth of MAHE. He has published extensively in reputed journals and continues to contribute actively to academia and professional societies. We are privileged to have him preside over this this occasion and this event. May I now request Professor Narayan Sabahit for his presidential address. Thanks.
Chief guest of this function, Professor John Henry, Professor Samir K. Nayogi, Dr. Cherian Varghese, other dignitaries on the dais, the participants of this international conference on operation research and decision sciences. Today, I am standing before you as an administrator, as a researcher, both. As an administrator, as a researcher, both, I am thankful to the mathematics. Today, what I am here, it's because of the mathematics. You may believe it or not. As an administrator, today, any decisions which I make, it's purely based on the data. The data which I get for anything which I analyze using mathematics. Probably I'm handicapped without, the mathematical tools to analyze the data.
As a researcher, yes, obviously I'm a civil engineer. I don't know whether any engineers are here. So basically a civil engineer works on the landslides. You know, landslides, it's things which happens, unexpected. Way back in 1990s, beginning of 90s, I was using the optimization techniques. So optimization techniques are very close to my heart. Of course, I used various methods, probably without which our areas not probably progressed to the level which it has progressed currently. Those were the days we had the mathematical, the algorithms and all those things. I used to write the programs. That time the programming language was Fortran 4. We used to use Fortran 4 to write the program. Though it was very challenges, a lot of challenges were there, but it was very, very interesting. So many problems we solved, which really predicts, at least to the extent of, the 90 to 95% accuracy using, the mathematical modelings. Today, if you look at any field, if you deep dive, you will see the mathematics. So much of powerful mathematics. Because of, mathematics, the other fields have come up, particularly engineering. That's why I like, the applied mathematics. We can use the mathematical tools for applications in engineering, medicine, as Cherian also told that about, public health. You take any area, mathematics is very much required. So that's the reason why we give a lot of importance for mathematics. In fact, this center was created for that reason, because a department most of the time concentrates on offering the programs, BTech programs, or maybe, supporting other engineering programs, master's program, PhD programs, research, all those things, they are tied up with, the so much of work in the departments. So we thought that let us create a center exclusively to work on, these areas, mathematical areas, and also conduct the conferences like this, the reputed national and international conference. So the right person was, the Prasad. He came forward, and I was, the mentor for this center, and he took this center forward. Today, it's one of the best centers in the university. We have many centers in the universities. Whether it is terms of organizing the events of this scale, or getting the funds. Mathematics, it's extremely difficult to get the funds, unlike the engineering, the fields. But still, we are getting good number of the funds from the government agencies, and he's very instrumental in getting all those things done in this last how many years? 5 years or 6 years roughly. So around 5 to 6 years back, we created this set. So the idea is to bring, the people who are working in mathematics, also particularly the applied mathematics, how mathematics can be applied in the field, particularly engineering and other fields, and see that, its application will take the dominance. So Dr. Prasad not only taken, this center to a very high level, also he has created the second level. I think today's people who are, I think, what's your Varun, right? Varun, and as well as I think Hari Krishna is also here. So they are, the taking this further, because time has come that, he has done enough, the Prasad has done enough, and now he has created the second line also. So thank you very much, Prasad, and really you have done wonderful work, and I am sure many people have, they are coming regularly for attending these conferences. The way in which he conducts the conference is really appreciable. So this campus is a multidisciplinary campus. I am sure many of you are visiting first time Manipal, including the chief guest himself is visiting Manipal first time. Sir, this is a large campus. It's a multidisciplinary campus. We have almost all programs. You just name it, we have it. Okay, please go around the campus and see. I'm sure organizers will make some arrangements. And please see what we are doing. Manipal is today number 4 in the country among this NIRF ranking. Just above 4, the first, second, and third, they are all public universities. So among the private, we are number 1 NIRF ranking. So we offer many programs and also almost all, the PhD programs in very, diversified areas. We also promote multidisciplinary research. Today, engineering faculties working with not only engineering, even mathematics faculties, they are working with, the KMC faculties, like doctors, dentists, pharmacologists, all those people, they are doing work together. It's a multidisciplinary campus. Please go around. We will make some arrangements to visit the campus and enjoy the stay in Manipal. Thank you very much for giving me an opportunity here to be here, and all the best for the conference, and have a safe, enjoy the stay here in Manipal. Thank you.
Thank you, sir, for highlighting the importance of the precision sciences as well as mathematical sciences to the August audience. We have before us Dr. Harikrishnan, co-organizing secretary of Icords 2025, to propose the vote of thanks. Over to you, sir.
Good afternoon, everyone. On behalf of the organizing committee, it is my pleasure and privilege to propose the vote of thanks to this August gathering. First and foremost, I extend our heartfelt gratitude to our chief guest, Professor Juan Martinez from Universitat Autónoma de Barcelona, for inaugurating this conference and gracing this occasion with his presence. Thank you, Professor, for your kind and inspiring words. We are deeply grateful to Dr. Narayan Sabayat, sir, Pro Vice Chancellor, Technology and Science, for presiding this function and releasing the abstract booklet. Sir, your wholehearted support and encouraging words have been a great source of motivation for all of us. We express our profound thanks to you. We would also like to thank the guest of honor, Dr. Cherian Varghese, sir, Director of PSPH Mahe, for honoring us with his presence and sharing his thoughtful insights. We thank Professor Samir K. Niyogi, sir, Chairman Scientific Committee, for his guidance throughout this conference. Thank you, sir. Our sincere thanks goes to the coordinator of CARAMS, Professor Manjuna Prasad, sir, for his invaluable guidance and support in organizing this conference. We extend our warm appreciation to all the plenary and invited speakers for accepting our invitation and enriching the conference with their presence and insightful talks across various disciplines. We gratefully acknowledge the partial support from ANRF DST, the government funding agency, in making this event possible. A special note of thanks to all the delegates, both in person and online, who have joined us from various universities across India and abroad, as well as the faculty members present here at Springer Nature. And also we thank the Springer Nature for their kind support. We also thank Mahe and MIT for their logistical support in facilitating the smooth conduct of this event. Also, we thank the head of the department, Civil Engineering, and in charge of KEF R&D Center and the caretaker of this conference hall for their help and cooperation in organizing this program at this venue. Finally, we thank the staff members, security personnel of MIT, and the media team for their efforts and support. Thank you for being with us today and contributing the success of this conference. Wishing you a great day ahead. Thank you.
Thank you, sir. With this, we come to the end of the inaugural function of Icords 2025. And next we have a photo session followed by tea, after which the technical sessions will follow. So I wish you all a pleasant stay at Manipal for the ones who have come to Manipal, and all of you a successful conference. Thank you. We'll be having a photo session right now. We'll have it here itself. Can I be covered? Okay. Yeah, we'll have it downstairs. Kindly join downstairs for the photo session. I request everyone to quickly join the photo session and follow the dignitaries for the path. I request everyone to be downstairs. This one, so that we don't delay our sessions further. You have a tea break after the photo session, so kindly be present for the photo session downstairs.
That's the photo session happening outside.
The one who removed the table should put it on. Yeah. Okay.
ಎಂತ ಮಾಡುದು ನನ್ನ ಅಪ್ಪ ಮಾಡ್ತಿರ್ತಿತ್ತು. ಈಗ ಅನೌನ್ಸ್ ಮಾಡ್ರು ಹೇಗೆ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗುದಿಲ್ಲ. ಅನೌನ್ಸ್ ಮಾಡ್ರು ಉಪಯೋಗ ಇಲ್ಲ. ನಾನ್ ಬೇಕು ನಾನ್ ಕಡೆಲ್ಲ ಬರ್ತಾರೆ. ಬಸ್ ಅರೇಂಜ್ ಮಾಡಿದ್ದು ಹೋಸ್ಟೆಲ್ಸ್ ಅಂತ ಎರಡು ಬಸ್ ಅರೇಂಜ್ ಮಾಡ್ಲಿಕ್ಕೆ ಎರಡು ಬಸ್ ಆಗುದಿಲ್ಲ ಅಂತ ಒಂದೇ ಬಸ್ ಆರ್ಗನೈಸರ್ಸ್ ಇಲ್ಲ. ವೈಟ್ ಬೋರ್ಡ್ David, use the tree. ಮತ್ತೆ ತಗೊಂಡು 4 ಗಂಟೆ 4 ಕಾಲಕ್ಕೆ ಅದು ಅಲ್ಲಿ ಮಕ್ಕಳನ್ನ ಹೌದಾ ಅಲ್ಲಿ ಅಲ್ಲ ಅಲ್ಲಿ ಇಡ್ಬೋದು. ಇಲ್ಲದಿದ್ರೆ ಅದು ಇದನ್ನು ಸೈಡಿಗೆ ಮಾಡಿ ಇಡ್ಬೋದು ಅಲ್ಲ ಇದನ್ನು ಸೈಡಿಗೆ ಅಲ್ಲ ಈಗ ಇದು ಬೇಕಾ ಈಗ ಮತ್ತೆ ಇಡಬೇಡ ಮತ್ತೆ ಇದು ಬೇಡ 4 ಗಂಟೆಗೆ 1 ಟಾಕಿಗೆ ಇಡಬೇಡ ಇಲ್ಲ ಸೈಡ್ ಮಾಡಿ ಇಡ್ತಾರೆ ಇಡ್ಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ವಾ? ಇಲ್ಲಿ ಸದ್ಯಕ್ಕೊಮ್ಮೆ ಇಲ್ಲಿ ಇಡು ಮತ್ತೆ ಅಲ್ಲಿ ತಕೊಂಡು ಹೋಗ್ತದೆ. ಅದ್ಯಾಕಂದ್ರೆ ಚೇರ್ ಸಿಗ್ಬೇಕು ಚೇರ್ಸ್ ಅಲ್ಲಿ ಕೆಳಗೆ ಇಲ್ಲ ಇಷ್ಟ ಇದು ಮಾರ್ಕ್ ಅಲ್ಲ ಉಂಟು ಅಲ್ಲ ಅಲ್ಲಿ ಎಲ್ಲರೂ ಬಂದಿದ್ದಾರೆ ಕಾಂಟ್ರಿಬ್ಯೂಟ್ 35-32 ಒಬ್ರು ನೋಡುದಿಲ್ಲ ನೋಡಿ 7 ಗಂಟೆಗೆ ಇರ್ಲೇಬೇಕು ಅವ್ರಿಗೆ ಇದೆ ಫ್ಲೈಟ್ 7 ಗಂಟೆಗೆ
stop it now. Very bad. To stop it 24. ಏನೋ ಯಾವ್ದೋ ಸೈಡು ಕಾಪು ಸೈಡು ಅಪ್ಪ ಯಾವ ಸೈಡು ಯಾವ್ದೋ ಸೈಡು ಯಾವ ಸೈಡ್ ಕೂಡ ಗೊತ್ತಿಲ್ಲ ಸಿ ಸೈಡ್ ಹೋಗಲ್ಲ ಸಿ ಯಾವ್ದು ಇಲ್ಲಿ ಬರುತ್ತೆ ಕಾಪು ಒಳ್ಳೆ ಅಪ್ಪಲ್ಲ ಅಪ್ಪ ಕೇರ ಆಗ್ತದ ಪೂರ್ತಿ ಕೆಲಸ ಮಾಡಲ್ಲ ಕಂಡ ಅವ್ರು ಪೂರ್ತಿ ಅವ್ರಿಗೂ ಮುಖ ಕೊಡಕ್ಕಾಗಿಲ್ಲ ಅವ್ರು ಹೇಳೋ ಅಂತ ಎಷ್ಟೇ ಆಗ್ಬೇಕು ಬಸ್ಸಲ್ಲಿ ಹೋಗ್ತಿರುವಾಗ ನಮ್ಗೆ ಒಂಥರ ಬೇಸಿಗೆ ಆಗುದಿಲ್ಲ ಆದ್ರೂ ಇದ್ರಂತ ಅಂದ್ರೆ ಈ ಬಾಲ್ ಡೆಲಿಗೇಟ್ಸ್ ಎಲ್ಲರೂ ಎದುರುಗಡೆ ಕೂರಿಸಿ 10 ಜನ ಕೂರಿಸಿ ಈ ಕಾಂಟ್ರವರ್ಸಿ ಮಾಡಿ ಆದ್ರೆ ಒಬ್ರು ಆಡ್ ಮಾಡ್ತಾರೆ ಎಲ್ಲ ಬೆಲೆ ನಾವು ಚೆಕ್ ಮಾಡಿ ಹಾಕ್ಬೇಕು ಅಂದ್ರೆ ಎಂತ ಹೇಳಿದ್ರು ಹೆಂಗ ಎಲ್ಲ just remember that we have kept it. ಪಾಪ ವೇಸ್ಟ್ ಯಾರೊಬ್ರು ತಗೊಳ್ಳಿಲ್ಲ ತರ್ತಿದ್ದೀನಿ ಅಲ್ವಾ ಇರ್ಬೇಕಲ್ಲಿ ನಾಳೆ ಸ್ವಲ್ಪ ಅದು ಇನ್ನು ಅವ್ರ ಪ್ರಾಬ್ಲಮ್ ಅವ್ರು ಇದು ರಿಸರ್ಚ್ ಏನಕ್ಕೆ ಬರಲೇ ಇಲ್ಲ ಮುಂಚೆ ಆಗಿದೆ ಅಂತ ಹೇಳ್ತಿದ್ರು ಅದಕ್ಕೆ ಅಷ್ಟೊತ್ತಿಗೆ ಬಂದ ನಾನು ಒಂದು 80 ಹೋದ್ರೆ ಮಾಡೋದಕ್ಕೆ How you are? Coming. Sorry, even 30 minutes. We are planning to.
Next, LS. UP Lab 01.
ಎಣ್ಣೆ ಮಧ್ಯಾಹ್ನ ಬರ್ತಾ ಕಾಂಡ ಬರ್ತಾ ಗೊತ್ತಿತ್ತು ಏನು ಬರ್ತಾ Okay. Then I have the list of So I'm supposed to read this? Yes. Just confirm.
He's saying that here.
Yeah, I know.
Yes, yes. You just try to do it. I'll be.
Yeah, that's one. No, but that also, already, I have it here. So I'll try to drop you not here. That's okay. I'll just write it down. Okay. When does it start? Actually, it should have started earlier, but now no one is there. We're going to wait. Probably a couple of minutes more. Yeah, just write it. Yeah, I just write. Yeah, then you take it.
Yeah, I have now. I guess that. Let's hear, let me. Because I, yeah, it's nothing. I can, yeah, I was thinking. Before that. That's fine. Okay, after that.
Yes, sir. Yes, sir.
But since it's delayed, we'll start from now.
Yes, sir. Yes, sir. Actually, it's 2 minutes fast.
No, it's long past. We are supposed to start at 3:15. Okay, so we start at 3:45?
No, we will start now, sir. We will immediately start.
Again. People come.
5 minutes,
nobody-
5 minutes max.
Yeah, 3:45 we'll start. Exactly. It's now
Sir, we
3:43.
will check the schedule, sir. How many sessions are? 3 are there now, sir. We will not be able to finish because they have a plan of going to.
I am going. And I have to finish here.
So we have a plan of going there and
So we
coming
start
back.
in 3 minutes.
Yeah, we'll start at-
35.
Yes, correct, exactly. 3 minutes we
We'll
start.
keep this as the time.
Yeah.
When the time? If you want to.
No, sir, we have to take.
Okay,
No, I'm supposed to start by 3:15. That is why we took the photo here. Otherwise, we usually take the photo there.
Yeah,
Ah.
I know.
Still likely we get delayed.
Afternoon, everyone. So I'm pleased to introduce Professor Murali K. Srinivasan, who is joining us from IIT Bombay. He's a leading figure in combinatorics, and his remarkable work includes studies on Eulerian generating functions of Q derangements and a wide range of contributions in the combinatorics of graphs, algebraic structures, and representation theory. He has been closely associated with CARAMS and continues to support its events and initiatives. He has also developed Maple programs for combinatorial applications and has collaborated with several renowned mathematicians across India and abroad. Over to you, sir.
Sorry for the slight delay in starting the session. So I'm delighted to welcome our first speaker, Dr. Sasmita Barik who's the professor at IIT Bhubaneswar. She did her PhD from IIT Guwahati, and then she did postdoctoral research at ISI Delhi and the University of Regina in Canada. Her research interests are combinatorial matrix theory and spectral graph theory. She currently serves as an editor of the SIAM Undergraduate Research Online. Today she'll be talking on the limit points of the smallest positive eigenvalues of.
Okay, thank you, sir, for introducing me. And thank you, Professor Manjuna, for inviting me for a talk here. Actually, this conference doesn't fit our area, but somehow I'm related to Professor Raghavan, sir. He is my great grandchild, you can say. So I'm the fourth generation. And so here, this talk is dedicated to him. And this will be on limit points of smallest positive eigenvalues of graphs. So smallest positive eigenvalue, again, it's a new parameter that we are studying. So I'll first introduce what is smallest positive eigenvalue. and what is the motivation behind considering this particular eigenvalue. And then we look for why I consider the limit points, and we look for the results that we had. So for this talk, my graphs are simple graphs. So we have a possible as one edge only, and that's undirected. So the matrix that I am considering for this talk is only adjacency matrix. So it's a natural matrix that has been related to a graph. So you will put the ith entry as 1 if I and j are adjacent, otherwise it's 0. So the way, like, because we are taking undirected, so the matrix will be a symmetric matrix, and the diagonal entries are 0, and all other entries are either 0 or 1. So since the trace is 0, we have the sum of eigenvalues equal to 0. So if there is a positive eigenvalue, that guarantees that there is a negative eigenvalue. So you can also order the eigenvalue because all the eigenvalues are here real numbers. So I take this ordering. Lambda n is the largest, and lambda 1 is the smallest one. And here lambda n is the spectral radius, so we denote it by rho g. And the smallest positive eigenvalue, that is the smallest one among the positive ones, that I consider here, that is the tau g. So some because students are here, so why we consider eigenvalues? Because eigenvalues tells something about the graph structure. It gives some information about the graph structure. For example, these are very preliminary things. Like if I add all the eigenvalues, it's 0. But if I take the squares of all eigenvalues, it's giving the 2 times number of edges in the graph. Similarly, if I take the cube of all and add them, and I get how many triangles are there. It's 6 times the triangles, number of triangles. Similarly, if I know that the second largest eigenvalue is -1, I know that the graph is complete. Like this, these results are there. The last one is important because it characterizes all the bipartite graphs. We call it the spectral characterization of bipartite graph. So if the spectrum is symmetric about origin, that means if lambda is an eigenvalue, then minus lambda is also an eigenvalue with the same multiplicity, then the graph must be bipartite. Now, talking about the smallest positive eigenvalue, and the mostly studied eigenvalue is the spectral radius, that is the largest one. Also, the least one also studied. But if I consider the smallest positive one, that its position is not fixed. It may take the value, like for the star, it is the largest one also. But if I take a arbitrary graph, its position is not fixed. So it will lie in between. And then our linear algebra techniques are like, we cannot use many things which we use usually to study the spectral radius. So if I take a graph which is non-singular means the matrix is non-singular. In that case, basically I'm avoiding the zeros. So my eigenvalues will be either positive or negative. And with that, if I add bipartite, then I know its position, and it's like coming if non-singular and bipartite and 2 m vertices, I know that the position is in m+1 position. So in that case, we know the position. So some techniques can be used to say something about this eigenvalue. Okay. So another thing that is important here is perfect matching. So a matching is a set of edges which are disjoint in the sense that there is no common end vertex. And if they cover all the vertices of the graph, it's a perfect matching. So we know that if a graph has a unique perfect matching, it's non-singular. So we targeted first that class. So the class of bipartite non-singular graphs which has a unique perfect matching, and we studied the thing. So I'll take this definition that will be used, that is the corona. And many people know, so if you take a graph and add pendants to each vertex, that's known as simple corona, which is, I'm saying here corona. So like I have a P4 and I add pendant to each vertex, that's the corona of P4. So this definition will be used. And why we took this eigenvalue to study? So if you look for a graph and that's non-singular, its adjacency matrix is non-singular, then we can think about how the matrix AG inverse is looking like. And if AG inverse is signature similar to a non-negative matrix, in that case we say that the graph is invertible. And AG inverse S means after making the signature similarity. If that matrix is some matrix that may not be with 0, 1, but that's non-negative, so we can assign with a graph. So that will be the associated graph. That's known as the inverse graph of G. So when the graph is invertible, the spectral radius of the inverse is nothing but the reciprocal of the smallest positive eigenvalue. So this tells that somehow the graph is related to, means graph structure is related to the smallest positive eigenvalue also. Another thing is the reciprocal eigenvalue property. As I told, for bipartite graphs, lambda is an eigenvalue, then minus lambda is one eigenvalue. So we had asked this question that which are the graphs with lambda is an eigenvalue, then 1 by lambda also one eigenvalue. Such graphs are well studied. Like if I take a bipartite graph and make it corona, that graph will satisfy that property. So for those classes of graphs, again, if I look for the spectral radius, that is same as reciprocal of the smallest positive eigenvalue. This gives also another motivation. And third is the chemical graph theory, where Huckel graph is defined. That's a graph theoretical representation of a molecule. And here, like if we look at the carbon conjugated system, so here vertices are the carbon atoms and edges are the pi bonds between them. So given this, I can define this is the corresponding graph. For these graphs, actually, if you take a non-singular bipartite Huckel graph, most of the Huckel graphs, they are bipartite. So if I consider non-singular bipartite Huckel graph, then the total pi electron energy is the sum of all positive eigenvalues twice. And the HOMO energy, that is the highest occupied molecular orbital, that is same as the smallest positive eigenvalue. And the LUMO energy, that is the lowest unoccupied molecular orbital, that is negative of tau j. And HOMO-LUMO separation that decides the reactivity of the molecule, that is can be approximated by 2 tau j. And HOMO-LUMO index, that is another parameter, that is same as the smallest positive eigenvalue. So this gives a motivation to concept these problems. And so Gutman and Gottschall, they had started working on this in 1985 also. So I'll tell a brief, like whatever developments are done. So basically, we are looking for minimizing or maximizing tau in certain classes of graphs. So it was started by Gutman. He conjectured that the path of order n that will take the smallest, like minimum smallest positive eigenvalue among all non-singular trees, and that was proved by Gottschall. And it was generalized to any tree, and the same path is taking the smallest, means minimum smallest positive eigenvalue among all trees. And Pavlikova and Jettini, they proved that if you take a corona of a path, that will take the maximum smallest positive eigenvalue in the class of all non-singular trees. And we had proved that the star will take the maximum smallest positive eigenvalue among all trees. And as I told, we first consider bipartite graphs with unique perfect matching, and that guarantees that the graph is non-singular. So here I'm taking Gn as the class of all graphs which are with a unique perfect matching and bipartite. And if when I'm taking bipartite unicyclic graphs with a unique perfect matching, that set is UN. And all bipartite unicyclic graphs with a unique perfect matching, those are U. And n is 2m here because we have a perfect matching, so our number of vertices is here. So what we observe that if you are looking for estimation in unicyclic graphs, then take a path, and if I'm looking for the minimum one, then take a path of order 2m and choose the vertices m minus 3 and m plus 2 and put one edge there. So that will create a 6 cycle. And this graph actually will take the minimum smallest positive eigenvalues among all graphs, unicyclic graphs with a unique perfect match. Similarly, if your like here in the earlier case m was odd, so here m is even, then you have to choose m minus 2 and m plus 3, and you do the same thing, or it will create a 6 cycle. So these two graphs will take the minimum smallest positive eigenvalue. But if we go for the largest one, then here, like for spectral radius, usually the star comes, but here it's coming the corona. So you take a path of order m-1 first, and then choose the vertices m-1/2, m+1/2 if m is odd, and you have to choose m-2/2, m/2 if m is even. And now add 2 more vertices. So it will have 2 vertices, and put this cycle. So with this 4 cycle, so these are the 2 graphs which are taking the maximum smallest positive eigenvalue among all unicyclic bipartite graphs with a perfect match. Now we looked at, so this I'm skipping. So we looked at the bipartite graphs. In the bipartite class, you take a matrix like this, take a lower triangular matrix, Bij, with Bij defined like this. It's a 0, 1 matrix, and Bij will be 0 if either I is less than j or I minus j is even, otherwise it's 1. So take that matrix and form this new matrix, that is 0, B transpose 0. So that will correspond to a bipartite graph. So that I am denoting by E2M. So E2M, like if I take E8, that is looking like this. So you can observe that it's obtained from a path by adding one edge between two quasi-pendant vertices. But it will change, the thing will change if I change the order. So this graph actually, in this class, actually, if you consider the bipartite graphs with a unique perfect matching, then you can contract the edges also. So here I have taken G1 is a bipartite graph with a unique perfect matching. Edge contraction means you just contract the matching edges and make it a vertex. So after edge contraction, you can see from G1 I am getting a graph which is not bipartite. But G2 is again bipartite with a unique perfect matching. After contraction, the graph is bipartite. So what Godsell has had proved that for connected bipartite graphs on 2M vertices, this E2M 2M vertices for which G by M means after contraction the graph is again bipartite. For those graphs, the minimum tau will be taken in E2M. So the graph I defined. We could prove recently that this will happen for all bipartite graph with unique perfect matching. This E2M will take the minimum. And if I look for maximum, then I'm taking a lower triangular matrix with full ones. So m square plus 1, m square plus m/2 non-zero entries. So then I'm defining again a similar bipartite graph. So I'll take B and B transpose, and I'm looking for the graph K2M, which has this adjacency matrix. So here I have drawn K8, and then nicely this graph, if I take the inverse, it's giving you the path. And this graph takes the largest, smallest positive eigenvalue among all graphs which are bipartite and with a unique perfect matching. So here, if I look at largest, means when I'm looking for maximum, I can give a bound also because I know the graph and we can calculate the value. But when I'm looking for minimum, I can give the extremal graph, but I don't have a bound because it's tending towards 0 when m is increasing. So then like we could not find lower bounds. We could give the extremal graphs for each m, but we could not find the lower bound. So then I thought that let us look at the limit point. And the limit point problem is not for graph theory. It started by Hoffman in 1972. He posed the question of looking for limit points of the eigenvalues of non-negative symmetric matrices with integer entries. So let A be the class of all non-negative symmetric matrices with integer entries. So let rho A denotes the spectral radius of the matrix A, which is lying in this class. So he took the set R. R is set of all spectral radius. Okay. And he posed the question that what are the limit points of R? So he observed this is very nice, and the proof is also nice that he observed that you don't have to consider all the integer matrices. You can restrict your matrices to 0, 1 matrices with diagonal entry 0. That means you have to consider only adjacency matrices. So the problem from matrix theory that we reduced to like graph theory, And he used also graph theory technique to get the limit points. So now the problem is you take any connected graph and take the spectral radius. You can define R rho as the set of all spectral radius. The question is reduced to this set and what are the limit points for this set. So Hoffman himself, like here, while defining limit point, we are taking distinct sequences. So we are considering graph with distinct spectral radius. The definition also I'll take for smallest positive eigenvalue. So for spectral radius, they were targeting to see like which numbers are limit points for that set. And if you take the golden ratio, root 5 plus 1 by 2, and then you take the square root of that, and so alpha is the golden ratio, then alpha to the power half plus alpha to the minus half, that's the number square root of 2 plus root 5. So this is known also the Hoffman limit value. So all the limit points which are less than equal to this number, those he characterized. And he observed that the smallest limit point for the spectral radius is 2. So basically, between 0 to 2, there is a gap. You don't have any point which is a limit point. Similarly, they also observed from 2 to square root of 2 plus root 5, there are certain points which are not limit point. But after that, means if you take this here or 2, that if you take a number which a real number which is bigger than or equal to square root of 2 plus root 5, then you have a sequence of graphs for which the spectral radius will converge to R. So every other point after this number is a limit point. So the construction of sequences, graph sequences for such limit points were done through trees. So it's not necessary to consider graphs. So you can have a sequence of trees. And those trees are also very nicely caterpillar trees kind of. So that way it has been considered. Now, what do prove that if you take any real number, then there is a sequence of graphs for which kth largest eigenvalue will converge to R. So if you relax like to any eigenvalue, then you have the sequence. So every real number can be a limit point. And so that was proved by Zhang and Chen, that every real number is a limit point for some eigenvalues of graph. And every complex number is a limit point for the eigenvalues of diagrams. So these two were proved. And Smith also characterized all the graphs for which the spectral radius is less than equal to 2, because those are not becoming limit points, they are finitely many only. So they characterized. Now this limit point thing was not restricted to adjacency matrix spectral radius only. Guo studied for Laplacian eigenvalues, the limit points. And for Laplacian eigenvalue, this problem for spectral radius is interesting because they're not getting easily the results, and many people are trying to get the limit points for the spectral radius. This problem is open and many are working on this. And for algebraic connectivity, that is the second smallest eigenvalue of the Laplacian matrix. For this, Cortland had studied, and he solved the problem fully. He proved that every real number is a limit point for algebraic connectivity. And for the normalized Laplacian matrices, also Cortland considered the problem. Here there is again gaps are there because for normalized Laplacian eigenvalue, they lie between like 0 to 2. So in 0 to 2, he had to study, and there also he observed that gaps are there. Now, limit points for spectral radius of sine graphs, that problem recently studied by Bellardo and Brunetti. They also found the intervals where the limit points are there, but again there are gaps. So what we can observe is for spectral radius of adjacency matrix, so there are gaps in between 0 to 2, you don't have any limit point, and between 2 to square root of 2 plus root 5, there are also gaps. For Laplacian spectral radius, again, this problem is unsolved, and like the people are working here, also gaps are there. For algebraic connectivity, any non-negative number is a limit point. For normalized Laplacian, this was proved that kth smallest eigenvalue, if you are considering all the limit points, will lie between 0 to 1. And if you are considering the kth largest eigenvalue, then the limit points will lie between 1 to 2. So, and that will cover both the like interval. It's not.
Try now. Can you try now? Can you try now?
So for spectral radius of sine graphs, as I told, there are also gaps. So we consider the smallest positive eigenvalue and its limit points. It was already started in 2018 by Chen and Chan. They had proved for trees actually that for trees we observed that the minimum smallest positive eigenvalue is in path. So if you take the sequence of paths, actually it will give you that the smallest limit point will be 0. Okay. And the largest limit point for smallest positive eigenvalues of non-singular trees, that will be root 2 minus 1. That comes because you are taking a corona, and corona has a spectral radius root 2 plus 1. You have to take the inverse of that, reciprocal of that. So that way the number is coming root 2 minus 1. So for us, we consider the unicyclic graphs. And here also the smallest limit point, you cannot consider the same path sequence because you are in the class of unicyclic graph. We consider it another sequence. And it was proved that smallest limit point is 0. And the largest limit point again root 2 minus 1. For the bipartite graphs, the smallest limit point will be 0 because paths are already there. And interestingly, the largest limit point came out as 1 by 2, which is the reciprocal of the smallest limit point of the spectral radius. And we also got the second largest limit point. That's coming, that number. So then we consider, like, let us take all smallest positive eigenvalues and look at that set. So R tau is the set of all all smallest positive eigenvalues. So it's take G as any connected graph and take tau G. Set of all such tau G, I'm taking R tau. So we asked the question that what are the limit points of R tau? And the smallest limit point is 0 because path sequence will be there. And what we could do is that if you have a number, real number, which is the smallest positive eigenvalue for some graph, then that must be a limit point for R tau. And finally, we could prove that take any positive real number, so that will be a limit point for R tau. So basically, including 0, any non-negative real number is a limit point for the smallest positive eigenvalue. We also considered the largest negative eigenvalue. So for that set, like R nu, that set, we could prove that any non-positive real number is a limit point for the largest negative eigenvalues sequence. So we conclude with this that R tau union R nu, that is tens in R. So this all happens.
I have just one question. So are there, you talked of roots of characteristic polynomial. So are there other polynomials for which associated to graphs for which these questions have been studied?
No, not yet.
Some magic
Like
polynomial.
independence polynomial, mixing polynomial, not yet studied. Because this is coming from the metrics, so directly they took the adjacency matrix and then. But for other polynomials, they have not yet.
Can you take some reference to the diagram? Take the adjacency matrix to full diagram.
Diagram problem? That's already here.
Here's only one. In general, the work for one.
He proved that every complex number is a limit point. That's what
That is. Yeah.
But like for like every, like if you consider the spectral radius and like that fixing one eigenvalue study has not been done yet. They considered recently sine graph.
Let us stand this speaker.
On behalf of organizing committee, I would like to thank Sir for chairing the session. Now I will request Sir to present a memento as a token of our gratitude and appreciation to the speaker.
So our next speaker is Deepthi Dubey. She is from the School of Natural Sciences, Shivnara Institute of Eminence. Her research includes linear complementarity problems, stochastic games, matrix analysis, with applications to economics and finance. She is also the author of a monograph, Mathematical Programming and Game Theory, published by Springer in 2018. So she's going to speak to us today on almost semi-monotone matrices.
Good evening, everyone. First of all, I would like to thank the organizer for inviting me. It's a great pleasure to be part of this conference, which is organized in honor of Professor Raghavan. Today, I'm going to talk on almost semi-monotone matrices, which is a joint work with my PhD student Bharat, who has recently finished his PhD. So the almost semi-monotone matrices were introduced by, or the notion of almost semi-monotone matrices was introduced by Professor P. Saxoner and his PhD student Megan Wendler in 2019. However, the semi-monotone matrices are well known in the theory of linear complementarity problem, which is one of the fundamental problems in the area of optimization, as it provides a unified framework to study linear programming problem, convex quadratic programming problem, as well as biometric scales. Even though a lot of work on semi-monotone matrices has been done, but still there is no efficient algorithm to check whether a given matrix is semi-monotone or not. So this motivated Professor T. Saxoner and his PhD student, Megan Wendler, to study and introduce the notion of almost semi-monotone matrices. What attracted us to this class of matrices was certain interesting matrix theoretic properties, like inverse of these matrices is always non-positive. And there was a conjecture made by Wendler in 2019, which says that if you have an almost semi-monotone matrix, it will be non-singular, its determinant will be negative, its adjoint will always be non-negative, and it's going to have exactly one negative eigenvalue corresponding to the positive eigenvalue. So in our work, we partially address this conjecture. However, the conjecture is still open. So, and it was natural for us to explore the role of these matrices in the linear complementarity problem. So I'll begin with the introduction, where I'll introduce or just recall the linear complementarity problem and certain matrix classes which I need in the subsequent discussion. In the second section, I'll talk about certain interesting. Yeah. So I'll be talking about certain. So I'll be talking about certain interesting matrix theoretic properties of the class of almost semi-monotone matrices, which were proved by Professor T. Saxoner and Megan Wendler as well as us. Then we'll talk about Wendler's conjecture and our contribution to it. And finally, we'll discuss the application of this matrix class in the linear complementarity theory. So let us begin with the introduction. So this is the general framework of a linear complementarity problem. In a linear complementarity problem, we are given with a matrix A and a vector Q, and the problem is to find a vector Z which satisfies the following three conditions. First two are just the non-negativity restrictions, and the third one is known as the complementary condition, which says if ith component of Z is positive, the ith component of Q plus AZ has to be 0. So the linear complementarity problem is, in short, is called as LCP, and the notation for it is LCP Q comma A. So if a vector satisfies the first two conditions, then it is called as the feasible solution. If it satisfies the complementary condition also, then it is called as a solution. So these are the definition of the solution.
Now note that every LCP is solvable whenever Q is non-negative, because then Z is equal to 0 will serve as a solution. So given a linear complementarity problem, we are interested in questions like whether the problem is going to have a solution or not. If it has a solution, what is the multiplicity of the solution? Is it going to have a unique solution, finitely many solutions, or infinitely many solutions? In fact, for the class of almost semi-monotone matrices, for certain values of Q, the LCP is going to have exactly 2 solutions. So that we'll see later. Yeah. So whether it is existence or multiplicity of the solution or algorithm to find the solutions, matrix classes plays an important role in this theory. One such matrix class is class of semi-monotone matrices. So we'll come to that later. First, let us just have a look at the application of linear complementarity problem. As I said earlier, linear complementarity problem provides a unified framework to study following optimization problems. In fact, these equivalent formulations are found to be very useful in developing the theory for LCP as well as for the other problems. This problem naturally arises in option pricing as well as portfolio selection in finance, optimal stopping, and market equilibrium in economics. Now, as I said, given a linear complementarity problem, most of the things depends on the underlying matrix, properties of the underlying matrix. There are more than 50 matrix classes which are studied in the literature of linear complementarity problem. Some were there already in the matrix theory but found to be useful in linear complementarity theory, and some were introduced specifically in context of linear complementarity problem. So again, one such class is the class of semi-monotone matrices. So I'll begin with the definition of a Q matrix. A matrix is said to be a Q matrix if the corresponding LCP is going to have a solution for all Q belonging to Rn. It is said to be a Q0 matrix if LCP QA is visible, implies it's going to have a solution. For the next definition, we need to recall the notion of principal minor. So given a matrix A, if you take alpha as a subset of index set, beta is also a subset of index set, then A alpha beta forms a submatrix. If alpha is equal to beta, then we call it as a principal submatrix and its determinant is called as the principal minor. So a matrix is said to be a P matrix if all its principal minors are positive. It is said to be a P0 matrix if all its principal minors are non-negative. Note that every positive definite matrix is a P matrix. However, under symmetry, these two classes are equivalent. For a P matrix, we have a very nice characterization in terms of linear complementarity problem. It says a matrix is P matrix if and only if LCP QA has a unique solution for all Q belongs to Rn. So this diagram summarizes the relationship between class of P, Q, Q0, positive definite, positive semi-definite matrices. The class of S matrices I have not introduced yet. So that is on the next slide. Another interesting class of matrices in optimization is the class of copositive matrices. The class of copositive matrices is the generalization of positive semi-definite matrices, and there is a whole field of copositive optimization where we need these matrices. So a matrix is said to be copositive if X transpose AX is non-negative for all X non-negative. Note that for the positive semi-definite, we want this condition to hold for all X belongs to Rn. It is said to be strictly copositive if the inequality is strict. It is said to be copositive of order K if every principal submatrix of order K belongs to that class. Then we have the definition of S matrix. A matrix is said to be S matrix if there exists X greater than 0 such that AX is also greater than 0. And then we have the definition of S0. Now we are ready to define the class of semi-monotone matrices. So a matrix is said to be semi-monotone. The notation for this class is E0 if for every non-zero non-negative vector X, there exists an index set K such that xk is positive and axk is non-negative. It is said to be strictly semi-monotone if the inequality is strict on the right-hand side. That means if xk is positive and axk is positive for some k. These are the example of semi-monotone matrices. Now, semi-monotone matrices are not only important from the linear complementarity point of view, this is also very important from the matrix theoretic point of view, as it contains several well-known matrix classes. For example, it contains the all non-negative matrices, it contains P-naught matrices, positive semi-definite matrices, and P-naught and the very popular co-positive matrices. So now let us discuss about the role of semi-monotone matrices in the linear complementarity theory. So if a matrix is semi-monotone, then the corresponding LCP is going to have a unique solution for all Q strictly positive. We know every LCP has a solution for Q positive, and that solution is trivial one. But there are LCPs which can have non-trivial solution also, but here we have only just one solution. For strictly co-positive matrix, we have the following result, which says that the following conditions are equivalent for a given matrix A. So if A is strictly semi-monotone, then the LCP QA is going to have a unique solution for all non-negative Q. Now, to study the class of semi-monotone matrices, the notion of almost semi-monotone matrices was introduced in 2019. However, the notion of almost type of matrices was introduced first time by Vallejo in 1986, and he introduced the notion of almost copositive matrices and almost strictly copositive matrices. And the motivation for introducing these classes was to derive a nice criteria for testing the copositive matrices. So a matrix is said to be almost copositive if all its proper principal minors are copositive, but the whole matrix is not. So following the same definition, the notion of almost semi-monotone matrices was defined, and a matrix is said to be almost semi-monotone if all proper principal submatrices are semi-monotone. However, there exists a vector x which is positive and ax is negative. For almost strictly semi-monotone matrices, we just want ax to be less than equal to 0. So, Tatsumras and Wendler completely characterized the 2 cross 2 almost semi-monotone matrices. So, if A is a 2 cross 2 real matrix, it is semi-monotone. It is almost semi-monotone if and only if it has the following form. So its diagonal entries are non-negative and off-diagonal entries are strictly negative. They also proved for a 3 cross 3 matrix, if all proper principal submatrices are semi-monotone, then A is almost semi-monotone if and only if its adjoint is greater than equal to 0 and determinant is less than 0. From here, we'll start the results which we have proved, and in between, again, we'll recall the results proved by T. Setsumu and Megan Wendler. So we proved that if we have an almost semi-monotone matrix, then each row and each column is going to have a negative entry. And an almost semi-monotone matrix cannot be a triangular matrix. There is an interesting result for semi-monotone matrices which says that if you have 2 matrices A and B, and if A is less than equal to B entry-wise, if A is semi-monotone, then B is also going to be semi-monotone. However, the same does not hold for almost semi-monotone matrices. So this is an example for that. But we proved that if you have an almost semi-monotone matrix A, and if B is less than equal to A, and all proper principal submatrices of B are semi-monotone, then B is also going to be strictly semi-monotone. We also proved that if a matrix is almost semi-monotone, then its Transpose is also going to be almost semi-monotone. If P is a permutation matrix, A is going to be almost semi-monotone. If and only if P transpose P transpose is also almost semi-monotone. If A is a matrix and D is a diagonal matrix, then A is almost semi-monotone. Then the following are equivalent. A is almost semi-monotone, DA is almost semi-monotone, and AD is also almost semi-monotone. For the next result, we need the notion of principal pivot transform. So given a matrix A, if alpha is the subset of index set, and A alpha alpha is a principal submatrix, if it is non-singular, then we can define a principal pivot transform of matrix A with respect to A alpha alpha, and the expression for that is given here. The Schur complement of A with respect to A alpha alpha is given by that expression. So in linear complementarity problem, the concept of principal pivot transform is very important, because for a linear complementarity problem, you can formulate an equivalent linear complementarity problem using the notion of principal pivot transform. And these two problems are equivalent in the sense if one has a solution, then the other one is also going to have a solution. And inverse is also one of the principal pivot transform for a given matrix. So that is very useful from the algorithmic point of view. So it was natural for us to look for whether the principal pivot transform of a almost semi-monotone matrix is going to be almost semi-monotone or not. Schur complement of your almost semi-monotone matrix is going to be almost semi-monotone or not. So answer for both of these questions are no. So we have an example here. The matrix is almost semi-monotone. However, its Schur complement is not almost semi-monotone. Now, the inverse of your almost semi-monotone matrix is non-positive, which is a Z matrix, and that cannot be almost semi-monotone matrix, because for a matrix to be almost semi-monotone matrix, its diagonal entries has to be non-negative. So again, it was natural for us to look for under what condition we are going to get the results that PPT of a almost semi-monotone matrix is almost semi-monotone, and Schur complement is again a almost semi-monotone matrix. So if we assume, if we take the assumption of Z matrices, so a matrix is said to be Z matrix if it's all of diagonal entries are non-positive. So if a matrix is Z matrix, and if we take Schur complement of that matrix with respect to A alpha alpha, which is a non-singular submatrix, then the Schur complement is going to be almost semi-monotone. Note that here A is also almost semi-monotone, and so is for the PPT. In fact, in this case, the matrix is also only going to have at most two PPTs, and both of them are going to be almost semi-monotone. It was proved by Wendler in 2019 that if you have an almost semi-monotone matrix, then A inverse exists and it is going to be less than equal to 0. We proved that if you have a matrix, all whose principal submatrices are semi-monotone, then A is almost semi-monotone if and only if its inverse exists and inverse is less than equal to 0. So this is both ways, but we have an additional condition there. Now we are going to talk about Wendler's conjunction. So the result was proved by T. Somras and Wendler for 3x3 matrices. So they proved that if you have a matrix A, if all its principal submatrices are semi-monotone, then A is almost semi-monotone if and only if adjoint is non-negative and determinant is negative. And then in 2019 itself, Wendler conjectured that if A is an almost semi-monotone matrix, then its determinant is going to be negative, adjoint is going to be non-negative, and it's going to have exactly one negative eigenvalue with positive eigenvector. So we found a counterexample, and this example shows that the second part of the conjecture does not hold. This matrix is an almost semi-monotone matrix, and it has exactly 3 negative eigenvalues. However, the first part of conjecture is still like we don't know about it. So we try to find some special conditions under which this first part also holds. So if we take the assumption of symmetricity, then we proved that the first part as well as the second part of the conjecture holds. That means if a matrix is symmetric, almost semi-monotone matrix, then the conjecture is true. Wendler also showed that if we have an almost semi-monotone matrix, then it is almost P-naught matrix for n is equal to 2 and n is equal to 3. However, for n is equal to 4, it does not hold. So again, it was natural for us to see under what condition this inclusion holds. So if we assume our matrix to be symmetric matrix, then for any general n, this relationship holds. Again, it was natural to find a condition under which these two classes are equivalent. So if we take the assumption of Z matrices, so if A is a Z matrix, then it is almost semi-monotone, if and only it is almost P-naught matrix. Yeah, in fact, it is true for a more general class than the class of Z matrices. So that class is known as satisfying the property plus plus. A matrix is said to be set to satisfy property plus plus if there exists a K-naught matrix, that is the intersection of Z and P-naught matrix X with positive principal minor such that AX becomes a Z matrix. So any Z matrix is it plus has property plus plus. The class of property plus the class of matrices satisfying property plus plus is complete. That means all its principal submatrices also satisfy that property. So we proved that under the assumption of property plus plus, these two classes are equivalent. In fact, we proved that under the assumption of property plus plus, the conjecture is true. So now we'll discuss the role of almost semi-monotone matrices in the linear complementarity problems, and I have just summarized few important results. So a matrix is said to be R-naught matrix if solution of the linear complementarity problem with that matrix and Q as 0 is the trivial, that is a zero solution. So we have proved that every almost semi-monotone matrix is in fact an R-naught matrix. We also proved that if we have an almost semi-monotone matrix, then for every Q non-zero non-negative, the corresponding LCP is going to have at least two solutions. And for Q strictly positive, the LCP is going to have exactly two solutions. One of them is going to be in fact positive. For any Q non-positive, non-zero, the LCP is not going to be even visible. So it's not going to have a solution. Further, again, we have a generalization of the class of Z matrices, which is known as hidden Z, and it is defined as follows. So you need two Z matrices X and Y such that AX is equal to Y becomes a Z matrix, and X and Y should satisfy that condition. So every almost semi-monotone matrix is a hidden Z matrix because hidden Z matrices are invariant under principal pivot transform. So inverse of your almost semi-monotone matrix is non-negative. That makes it a hidden Z matrix. Now hidden Z matrix belongs to the class of Q-naught matrices. So this also belongs to the class of Q-naught matrices. However, for any negative Q, our LCP is not even visible when we have A as an almost semi-monotone matrix. So it belongs to Q0 minus Q. So with that, I end my presentation. So still the main part of the conjecture is open, or the first part of the conjecture is open, that under various conditions we have proved the conjecture, but still the main part is open, that is its determinant of your almost semi-monotone matrix is negative and adjoint is going to be non-negative. So with this, I end my talk. If you have any questions, you can ask.
We might get that kind of question. So here we have gone to almost same one. I'll give a suggestion, no, which you can do. So you can one thing you can extend it for exact order to or exact
Yeah.
And so many of the results that
So, yeah, we have done that and we have recently communicated that paper.
Communicated.
Yeah. Like, yes, 2 days back.
many of the results that taken that whatever holds for C naught, that it's almost C naught. So many of the things that idea comes from there.
Yeah, the idea of definition comes from there, but here, like, we have different.
And third thing is that it will be interesting to note, even for fully semi-motor medicine, that so under what condition, no, that all PPT also will be semi-motor. Because there we consider only the class E0A. So that under what condition, like the way you have done for almost T1. Under what condition that a semi-motor matrix.
Yeah, the PPT is going to be semi-motor.
So that is not investigated. And those will be very useful. And yes, that even that if you see the go back for the co-positive matrices, that there are a number of people who are working on that trying to characterize the inverse co-positive matrices. So similar things can be extended for PPT when you can look at it for your next PhD student.
Thank you, sir.
So let us thank the speaker.
I will request sir to present a memento as a token of our gratitude and appreciation to the speaker.
So I'm very happy to introduce our next speaker, Dr. K.C. Kumar from IIT Madras. His research covers a wide range of topics, including infinite linear programming, generalized inverses, and linear complementarity. He is an enthusiastic educator. He is well known for his NPTEL course on linear algebra, and he has also mentored numerous students. He has had a long-standing and valued association with parents in contributing meaningfully to its academic initiative. He regularly reviews scholarly articles in his field and contributes actively to the academic community. So today he will speak to us on the maximum determinant positive definite completion of.
So you have to take something has happened here.
There's no signal lost.
While pulling it, no?
Yes. Thank you for the introduction, and I would like to thank Professor Neogi and Manjunath for the invitation. This is a pleasure to be part of Professor Raghavan's 85th birthday celebrations. I was hoping that I'll meet him in person. Only after coming here, realized that it's only online that we are going to meet him. Raghavan has been associated with IIT Madras for a long time, along with his alter ego, if I may say, Professor T. Parthasarathi, and we have had every time he comes to India, he, of course, his house is in Chennai, he comes there and gives a talk in IIT Madras. He's a walking encyclopedia, always has a touch of humor, and there is so much of life lessons that we have learned from him.
So,
So-
can tell you what?
Game theory work in IIT, no. Yeah, we haven't. And when the second announcement of this conference came on May 22nd, I was frantically looking at one of his papers, which appeared in Linear Algebra Application 1981. It also appeared in this book, Non-Negative Matrices, where he proves results on non-singular M matrices using game theory results. And I was just looking at possibilities, but I couldn't find much time to do that. But then I thought I should participate in it, so I should mention some optimization problem in my title. But it's rather deeply connected to what I am doing presently. So that's what I'm going to present today. So thanks for the invitation.
So those results are extended by TP afterwards. Lot of things that which appeared in linearity.
Yeah, those were extended by Gowda and Ravindran and for the linear transformation.
Even P. Pakistan, Murthy and all.
I see.
Lot of exercises.
Okay, about that.
Similar lines. Even
So-
we have also something. We used to give also only that game theory kind of interpretation to make Jeffrey happy. No? The other way of doing it.
Yeah. So the first few pages will be recalling what is the value of a game and
Right.
yeah.
Right. And that used to be bored. After some time, we used to feel bored. No?
Yeah. So it was yeah, you used it to impress the referees. Okay, so the maximum determinant positive definite completion. So this is something that I have tried to understand in the past couple of months or so. I happened to look at one of Gilbert Strang's old videos. This is about 7 or 8 years ago. I just happened to look at this where he discusses 4 applications of the tridiagonal matrix thing. So where does it arise? And the very first problem concerns what I'm going to talk about. Then I did a quick survey, and sometimes it's very depressing that you think that there is a new problem that you have found out. You dig deeper, you will see that there is so much that has been done already. So do I have a new problem? I think we were able to find out some new problem a while ago. The connection is something that I understood only recently. That's this talk about. So the maximum determinant, positive definite completion. Positive definite completion, what is the problem? So let me give the definition. And given a partial symmetric positive definite matrix, I left that thing. It must be positive definite. Partial means that only certain entries are specified. We need to fill the matrix with the rest. The rest of the entries of the matrix need to be filled, and you impose some condition. In this case, the condition is, does there exist a symmetric positive definite completion? That's the question. Does there exist a symmetric positive definite completion? So in order for the matrix to qualify even for this question, it must already be a partial symmetric positive definite matrix. I'll try and discuss some examples to make the discussion clear. Yeah, look at the first one. This is a symmetric matrix. The 3 diagonal entries have been specified. I am asking what should be these 2 entries, the red question marks. What should be those entries in order for this matrix to have a positive definite completion? So what I'll do is I'll post this as a one variable problem. So I put an alpha here and then ask what are the conditions that alpha must satisfy in order for this matrix to be positive definite. It's symmetric, so it's the same alpha that should appear on both sides. And then what are the conditions on alpha? What are the conditions for a symmetric matrix to be positive definite? Principal submatrices must have positive determinant. So the conditions are these. Alpha square must satisfy these 2 conditions. First one, alpha square less than 4. The other one is 2 minus alpha square plus alpha is positive. That's a determinant. The second condition comes from the determinant being positive. The first condition comes from omitting the second column and the second row. That 2 by 2 principal submatrix must be positive. So there are infinitely many solutions for this problem. You can take alpha to be any positive fraction. For instance, alpha equal to 0 works. Alpha equal to 0 works. Any positive fraction is a solution. So there are infinitely many solutions for this problem. There are infinitely many positive definite completions for a partial positive definite matrix which has the structure. So what is the structure? There is something special here. There is a tridiagonal structure, principal diagonal, super diagonal, subdiagonal. I'll look at another example just to kind of understanding what is going on here. But remember that there are infinitely many solutions for this problem. I would like to impose another condition for me to give uniqueness. I'll impose this condition. The condition is the determinant must be the maximum. So if you look at the argmax determinant, I think the point is not working. The argmax determinant for A alpha is 1 by 2. One variable problem, derivative 0 and second derivative negative, you get alpha to be 1 by 2. So you can go back and have I done that? Yeah. I'll go back and substitute this alpha, that's 1 by 2, and then find the inverse of that positive definite completion corresponding to this maximum value. The inverse is tridiagonal. The inverse of such a matrix is tridiagonal. Okay. Right. So this is one example. Let's look at another example where I have allowed for one more entry to be non-specified. I'll again want to look at the general solution for this problem, positive definite completion for this problem. So I have two variables this time, alpha and beta. The question mark means that those are things that need to be filled up, imposing this condition. So I have two variables, alpha, beta, then I have these conditions that must be met. Alpha square, beta square, both are strictly less than 4. And then there is this relationship between alpha and beta. Alpha square plus beta square plus alpha beta is less than 3. This problem again has infinitely many solutions. Alpha equal to beta equal to 0 is a solution. Alpha equal to beta positive fraction is a solution, etc. Among those, what is the one that has the maximum determinant? So I can go back and substitute. I'll leave it for you to verify that after substituting. That is, I look at now A0, 0, 0, alpha equal to beta equal to 0 is the unique matrix whose determinant is the maximum among all the positive definite completions. And you look at alpha equal to beta equal to 0, compute A inverse, it's again a tridiagonal matrix. I'll leave that for you. It is block diagonal, in fact. Yeah, so this is the determinant, and you observe that in this case, it's also tridiagonal. So this is a part of a general phenomenon which is stated in the following thing. So this is Dim and Goberg, Israel Goberg and H. Dim. This paper appeared in 1981. There is an article by Charlie Johnson, Matrix Completion Problems, a survey. It appeared in an AMS proceeding, 1990. And he mentions that Kara Theodori and Feyer have solved the Toeplitz case long ago. And this is a generalization of that. So what is a Toeplitz matrix? A Toeplitz matrix is a matrix which has a property that along all the diagonals you have only constant values. So they had considered the Toeplitz case and they have solved this problem. This is a more general situation. So how does it work? How does it work? The problem is the keyword is banded. You start with a banded symmetric partial positive definite matrix. Then this is the general phenomenon, particular cases of which I have illustrated earlier. Yeah.
What's a partial positive determinant?
Partial.
Already you can't say.
Not all entries are specified, but the matrix must qualify in order to be completed to a symmetric positive definite matrix. So it must already have those. See, for example, in the previous.
Diagonal cannot be 0.
Diagonals cannot be 0, cannot be negative.
Whatever
you can determine from the matrix is the principal, minor, positive, etc. Those conditions must be satisfied. This must qualify to be is an admissible matrix in order to be completable, and then such a matrix is called a partial matrix, can be completed. That's the question. So this is the result. You start with a banded matrix, banded symmetric partial positive definite, then it has a positive definite completion. Among such positive definite completion, there is a unique one with the maximum determinant. The maximum determinant problem has the property that the inverse is tridiagonal. That is hidden in this tridiagonal. it has at most the same bandwidth as the original matrix A that we started. Now, there are several generalizations of this. This is what I told you. Sometimes it's a bit depressing if you look at old results. I also see, I mean, we have become techno addicted people. I watched some political YouTube videos. There was something that popped up. You don't know. I mean, you call it coincidence or luck or whatever. This was about Nicolae Ceausescu. He was a Romanian dictator in last century.
Yeah. பேசலாமா? ம்? Yeah. இதுக்கு அடுத்தது. आमायन्तु ब्रह्मचारिण स्वाहा विमायन्तु ब्रह्मचारिण स्वाहा प्रमायन्तु ब्रह्मचारिण स्वाहा दमायन्तु ब्रह्मचारिण स्वाहा क्षमायन्तु ब्रह्मचारिण स्वाहा ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यङ्करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्तिः शान्तिः शान्तिः. My mother taught me how to count up to 20 with இந்த படத்தை எடுக்கணுமே, இந்த படம் இல்லாம படித்தேன்.
They can't see that.
Yeah.
Just you.
With my two hands, my father taught me to memorize multiplication table using Indian currency. Indian currency was split into 16 annas and 12 pies. 16 annas made 1 rupee and 12 pies made 1 anna. By age of 6, I knew how to recite all the multiplication tables I times j for I and j 2 to 16, both backwards and forwards. My mother I studied up to 5th grade at Samarao School, where my 2nd grade teacher was Miss Rajalakshmi and 4th grade teacher was Mr. Ramaswamy. Most kids wanted to climb up and down the classrooms. Exams were conducted by teachers reading questions out loud and children answering them on slates. The teacher would correct each slate and write the total score. Students could beg teachers to increase the scores. My 78 would be changed to 88. My friend Rangarajan's 38 would be changed to 88. We both felt happy, and our parents were happy, not knowing the true score. For the 6th grade, I attended the National Boys High School. My greatest inspiring teacher in science, math, geography, and in general discipline was our 5th grade teacher, Mr. Duraraj Pandian. He would spend his personal fortune to develop science experiments bringing caterpillars from home to show how they develop into butterflies, all carefully kept in an almirah with drawing papers, color pencils, etc. He would paste pictures on the walls with ships traveling the globe, slowly vanishing to prove that the earth is round. He would teach us to sing Tevaram of Jnana Sambandar in traditional music during group drills. On February 22, 1950, for being first in my class, he gifted me with a 200-page notebook, a quality pencil, and an eraser. For 7th grade, I attended Hindu high school and for the first time faced tough competition from brilliant students like V. Ramachandran, V.K. Srinivasan, T. Parthasarathy, S. Ganesan, Achal Krishnan, Ramamurthy, V. Gopal, and so on. As the number one student out of 7th grade H section, consisting of nearly 50 students, my score of 207 out of
stopping and resuming later, but
Sir, good evening or good night. I don't know, sir. Sir, Raghavan sir, can you hear us?
it'll be good morning.
Yeah.
Yes, sir. So there is one talk by Shivakumar sir is going on.
Okay.
Can we resume in another 5 minutes, sir?
That's fine. Let him finish and then I can start.
Okay, sir. We'll start in 5 minutes, sir. Thank you, sir.
Okay. Thank you.
Yeah, so there's a triangle property defined purely in terms of the entries of the matrix. Start with a matrix whose diagonal entries are all non-zero except possibly the first and the first one. Then you say that A possesses the triangle property. If this condition is satisfied, Aij is Aik, Akj by Akk, whenever K is an index that lies between I and J. Now, this is the reason why you want, see this denominator Akk, K takes the values between 1 and n exclusive. And so you impose this condition that those partial diagonal entries are non-zero. So this is triangle property. There is a reason as to why this is called triangle property, etc. This was introduced by Barrett. This is an example of a matrix that possesses the triangle property. I'll leave it for you to verify. There are several examples. There are several examples of matrices possessing the triangle property. I've just listed a few here. It's an increasing order of generalization. I've looked at a certain band. The two examples that I looked at where the property of those examples that the inverses are tridiagonal. Matrices whose inverses are tridiagonal. So that's something that I am looking at. So this is the result that was proved by Barrett. Take a non-singular matrix. This needs to qualify to be a triangle property matrix. So then this matrix has a triangle property if and only if the inverse is tridiagonal. So on the one hand, you have a structure property. On the other hand, you have a property that's defined purely in terms of the entries of the matrix. How is this problem connected to the previous one? So, but before that, here's an illustration. The example that I gave you is an example of a triangle property matrix, which is also non-singular. You can verify that the inverse is tridiagonal. Just a numerical example here. Where do we go from here? So, I need to give a relationship to what we were doing earlier. Look at the matrix A alpha. The first example. Look at the matrix. This matrix has a triangle property if and only if alpha is half. What is this value of alpha? This is the value of alpha for which the determinant is a maximum. So this is the connection between these two objects. So this is an illustration of the result of Barrett in the case of the example that came up in the PD completion problem. Similarly, the next example, the maximum determinant happens when alpha equal to beta equal to 0, and that's precisely the case when the matrix has the triangle property. You can verify this. There's alpha is a constant times beta, beta is a constant times of alpha. So alpha equal to beta equal to 0 is the only value for which triangle property holds. Where do we go from here? This has taken several directions. So what is the typical problem? The typical problem is the following. You have some properties on the entries of a matrix. Assume it's non-singular. There is a property on the inverse. The inverse, there is a there is a structural property on the inverse, there's a property on the entries of the matrix A. So there have been several results which have taken this general problem. For instance, what are those matrices, non-singular matrices, whose inverses, the graph corresponding to whose inverses are simple cycles? Just one problem to mention. There are several such problems. We have also worked at one or two such, but what I'm going to give you quickly in the next few minutes is I would like to look at the problem when the matrix has triangle property, but it's not non-singular. So it's a singular matrix, it's not invertible. I would like to ask the question for the Moore-Penrose inverse. What happens to the Moore-Penrose inverse? A is a singular matrix possessing the triangle property. The Moore-Penrose inverse always exists for all matrices. Does the Moore-Penrose inverse have the property that it is tridiagonal? So here is a quick definition of the Moore-Penrose inverse if you are looking at it for the first time. It's a unique solution of these four equations. These are called Penrose equations. Unlike the usual inverse, the Moore-Penrose inverse exists for all matrices. It's a consequence of the singular value decomposition. Bapat also has written a paper which appeared in Resonance some 15-20 years ago, 10 different proofs of the existence of the Moore-Penrose inverse. Why is the Moore-Penrose inverse important? If you look at the system Ax equal to B, when A is invertible, x equal to A inverse B is a unique solution. And look at x equal to A dagger B. So A dagger is a notation for the Moore-Penrose inverse. Look at Ax equal to B. For the system Ax equal to B, look at A dagger B. This A dagger B has the following optimality property. So what are the properties? If the system Ax equal to B has a unique solution, then that unique solution is given by A dagger B. If the system Ax equal to B has infinitely many solutions, among all those infinitely many solutions, the one which is closest to the origin is A dagger B. If the system Ax equal to B does not have a solution, then there is a least square solution. That unique least square solution is given by A dagger B. If the system is inconsistent, has infinitely many least square solutions, among all those infinitely many least square solutions, the one that's closest to the origin is A dagger. So this completely answers, the question which is analogous to x equal to A inverse B. So it's important from that point of view. There are several ways of defining. This is one way of defining. As I mentioned, you can look at Bapat's paper for the other equivalent definitions. These are some quick instances, but I think I'll skip it because I want to go to the theorem corresponding to triangle property and inverse being tridiagonal. So A is a singular matrix with possessing the triangle property. Is A dagger tridiagonal? The answer is no. This is an example of a matrix, rank 2. This has triangle property, but the group Moore-Penrose inverse does not have the tridiagonal property. But if you look at this matrix, this also has triangle property. It's singular. Its Moore-Penrose inverse is tridiagonal. So what are those matrices for which you can recover the result of Barrett? And how do you connect it with the maximum determinant positive semi-definite completion problem? How do you connect it to the maximum determinant positive semi-definite completion problem because the matrix is singular? So positive semi-definite completion, there is some recent result. Just about 4 years ago, I could trace an archive paper. There are some results where one can talk about the notion of a generalized determinant. There are some partial answers. The generalized determinant can be maximized if you look at the singular case. Is the one that's maximized if you look at the singular case. I'm just going to stop at this slide. The maximal rank case, I just wanted to show some of the recent results that we have got. A possesses a triangle property. Is A dagger tridiagonal? Answer is no. The answer for the converse is also no. A dagger tridiagonal. Does A possess triangle property? Answer is no. But we have completely solved this problem. These are some of these special situations. I think, I'm done. So there are two works that we have done in this connection. The first one appeared in Special Matrices. This is something, the last one is a paper that we have communicated. Tim and Goberg's paper that I mentioned, extending the very first possible extension, the PST completion problem after Kara-Theodori and Feyer, that appeared in 1981. And the one that I talked about is a Barrett's theorem on inverses of tridiagonal matrices. This is a vast area, but there are some interesting problems. I would like to stop.
So is a new student?
Granthi is my new student. Yeah. Thank you.
So you if you bring out all things, something will come out.
It does, yeah. Yeah. There's so much,
So
and you can always find new problems. That's I think that's a motivation.
the way you look at it.
The way you look at it, yeah. But as I told you, no, it's hard work meets luck.
So let us thank the speaker for an excellent job.
On behalf of the organizing committee, I would like to thank Sir for chairing this session. Now, I will request Sir to present a memento as a token of our gratitude and appreciation to the speaker.
May I request Dr. Niyogi to actually present the certificates to Dr. K.C. Shubu.
Thank you.
So I request Raju or Tirupati also to get his certificate. I request Niyogi sir to actually present the certificate to Raju sir. Thank you, sir.
They might be waiting for us. You will be on the same time. They are really suffering because you are going.
Now I request Dr. Satmita Parikh to actually continue the session.
Sir is there, but he did not switch on his video. So whenever he switches on, he will. He said to
Switch it.
yeah, not 20 minutes. Yes. He has switch on.
I will request sir to run on the video.
Yeah, don't delay.
Okay, so sir, can you see me? I'm Sosmita here. Raghavan sir?
Hello?
Yeah,
Yeah.
I'm Sosmita here.
Can I start?
Yeah, I'll introduce you first and then start.
Yeah.
Here we have our truly honored speaker, Professor T.S. Raghavan. So he is a emeritus professor in University of Illinois, Chicago, and over 60 influence research papers that also in three broad areas like game theory and matrix theory operation research. Sir has contributed a lot for the mathematics discipline, and he has been an integral part of Kerams family from last few years. He organizes the camps for the students, that is the Gurukul, which is like for many students it's very much helpful. His research contributions to zero-sum games, stochastic models, and policy improvement algorithms. So he is a globally respected scholar, and we are privileged here to have him for a talk today. And he will also speak later tomorrow, and day after tomorrow is dedicated to him. So welcome, sir. You can continue.
Okay. Om Sahanavavatu Sahanau Bhunaktu Sahaviryankaravavahai Tejasvinavaditamastu ma vidvishavahai Om Shanti Shanti Shanti. Let God protect me as a teacher and you as my student. Let Him stimulate the power of our mental thinking process. Let us jointly work together with full devotion. Let the knowledge we learn together be useful to us. On no account should we develop any mutual hatred. My mother taught me how to count up to 20 with fingers on my two hands. My father taught me to memorize multiplication tables up to 16 using the Indian currency, which in those days consisted of 16 annas and 12 pies. 16 annas will make a rupee and 12 pies will make an anna. So basically, he was training me to memorize I times j, where I and j are 2 to 16, backwards and forwards. I studied up to 5th grade at a particular school, and many of us were interested in playing more than learning. Exams were conducted by teachers reading the questions out loud, and there was no question paper. He will be reading from walking around and telling this question, and children will be answering them on the slates, and the teacher would correct the slate and write down the total score. As students, we could beg teachers to increase our scores. For example, once my 78 was changed to 88, my friend Rangarajan's 38 was changed to 88. It didn't bother either one of us. We were both happy that we got the same score, and our parents were also happy not knowing the true score. My greatest inspiration in those days was from my 5th grade teacher, Mr. Duraraj Pandian. He would spend his personal fortune to develop science experiments, bring caterpillars from home to show how they develop into butterflies, all carefully kept in an almirah with drawing papers, color pencils, etc. He would paste pictures on the walls with ships traveling the globe, slowly vanishing to prove that the earth is round.
Sir,
He would sing Tevaram of Jnana Sambandar in
Excuse me?
traditional
Sir,
during.
Raman sir.
Yeah.
Sir, I think you are trying to share one screen and then it is not visible to us.
Yeah. What should I do?
You'll have to share the screen, sir.
Yeah.
Now we can see only the iPad screen actually. Yes.
Okay.
Yeah, now it's coming. Thank you.
Is it okay?
Yes, sir. Please go ahead.
Yeah.
Sir.
Okay. He would spend his personal fortune to develop science experiments, bringing caterpillars from home to show how they develop into butterflies, all carefully kept in an almirah. He would teach us to sing Tevaram on February 22, 1950. For being first in my class, he gifted me with a 200-page notebook, a quality pencil, and an eraser. For 7th grade, I attended Hindu high school where I was facing for the first time a tough competition from brilliant students like V. Ramachandran, V.K. Srinivasan, T. Parthasarathy, S. Ganesan, Achal Krishnan, Ramamurthy, V. Gopal, and so on. As the #1 student out of 7th grade H section, my score of 207 out of 250 was just nothing compared to V. Gopal with 248 out of 250. And in the same class, T. Parthasarathy with 229 out of 250, even though it was way higher than my score. In fact, he was 4th in Gopal's class. That's the joke of it. A. Krishnan and T. Parthasarathy were my neighbors just a street away, so I was keen on competing with Parthasarathy, but we found a common interest. My classmate Narayanan's brother, Chandru, surprised me with the fact that any two-digit number ending with 5 can be squared very easily. He said, suppose say 65 times 65, change 6 to 7, multiply 7 times 6, 42, simply always write 42, 25. We were both on quickly solving the product for any two-digit numbers ending in 5. So this was our so-called initial research project with T. Parsarthi. How about 35 times 65 or 75 times 95? We found the first law. Outcome will be ending in 25 if the sum of the two tenth digits is even and will end in 75 if the sum is odd. For example, 75 times 95, something end with 25. 65 times 35, something end with 75. We were intrigued by all sorts of math puzzles, and we would spend many evenings with each other, commonly found secret solutions, and we used to be very careful that it should not be revealed to other students. And Pacha had the LG Perengayapoti, Asafoetida box, in which he would keep all our solutions. Pacha's father was a math teacher for high school. He was a high school teacher in our own school and was exposed to Euclidean geometry. Pacha was exposed to Euclidean geometry around the 9th grade. My father was a Sanskrit Pandit, and obviously he had no skills beyond arithmetic. My elder sister's husband, who was jobless after marriage, was my true inspiration for Euclidean geometry problems. The book Pierpoint on Euclidean geometry was the book with challenging problems. In 10th grade, the students have to make either getting into geometry and algebra type or pure ordinary arithmetic type. So you end up with the careers. If you have not chosen geometry and algebra, you end up with careers like accounting, pharmacy, medicine, law, botany. If you choose composite math, then you end up in engineering, statistics, banking, actuarial science, or compete for Indian Administrative Service. We, Gopal and others, were not able to keep up to the composite math. And in our school, from our school, Pacha and myself, we were among the 13 students admitted into the first ever batch for BSc in statistics at Loyola College. We studied MSc in statistics from Presidency College and moved on to ISI for our PhD. We practically were into identical research interests from our BSc days. In 1966, I submitted my PhD thesis, and even before it was printed, Professor C.R. Rao received a call from Professor George Barnard, a famous statistician from University of Essex. He was in need of a young PhD to teach statistics and probability. Based on just the instantaneous oral recommendation of Professor C.R. Rao, I was given a lecturership there. Yeah. The university environment at Essex was quite congenial. But however, many migrants coming from Africa with a British passport as British citizens faced much political commotion created by Mr. Enoch Powell. I decided to move to USA due to the discrimination we encountered at shops and stores. Thanks to Pramod Pathak, I joined UIC's math department in 1969 as an assistant professor with the full support from Professor Joseph Landin, the department head. I spent my time developing new undergraduate and graduate courses in game theory. In 1972, I was promoted as a tenured associate professor, and in that same year, Pacha came from India and joined us as a visiting associate professor from ISI. I had worked on completely mixed non-zero-sum 2% games earlier, and Pacha was keen on working with me on completely mixed n% games. That was the starting point for basic. Yeah. Hubert Chin is my first PhD student. Chin was a graduate student from Taiwan. He had completed his course and prelim requirements. He was keen on working in game theory. He took my undergraduate course in game theory and graduate course on the theory of games and statistical decisions. So with Pacha, when we started to work on equilibrium set and their nature for completely mixed n% games, we decided to give the same problems as open problems to Hubert to work independently. We were working together. Hubert was working independently. We could find a completely mixed 3% game with the two equilibrium strategies when n1 is 3, n2 and n3 are 2. We were debating on the uniqueness for n1 equals n2 equals n3 equals 2. One day, Pacha came up with a simple counterexample and demoralized me immediately. How I missed such a simple thing. After a month, Hubert came to us and claimed that he had an intuitive proof for the uniqueness. By his methods, he checked Pacha's counterexample and showed that we have mistaken and it has an equilibrium where one player skips a pure action. Of course, we were both happy and were ready to attack and supply formal proof for a more positive theorem. In fact, the other one is once you have a counterexample, it is useless. Then that problem doesn't have much value. Only positive results have value. So we were trying to construct a positive proof. So problem was first reduced to only matrices with just to, you need to associate a 3-row 4-column matrix and all the signs are either positive or negative, and there were 4096 matrices and many of them are out of question. And we had to eliminate those which can be proved as not completely mixed. And there was a physicist from the University of Chicago, Dr. A.V. Lakshminarayanan, who found that it is enough to prove for 762 cases. They fell into roughly 6 equivalence classes. We could use all topological arguments to argue that each one can be settled. So we worked out ruthlessly all the details. We submitted the paper, and the paper attracted attention of Professor Reinhard Zelten at Bielefeld. Zelten, as you know, was the first Nobel laureate with John Nash and John Harsanyi. In a 21-day workshop in game theory, the three of us were invited to present this work. We also had an open problem, namely to check for the uniqueness of the equilibrium for an n% completely mixed game, where each player has exactly 2 pure strategies. In a very ingenious paper, Buell is from, I don't know the name of the city, in Russia, constructed a 6% game where each player has 2 pure strategies and the game completely mixed, but with a continuum of equilibrium strategies. Thus, he ruled out our conjecture on the uniqueness. And in fact, Lord Shapley told me that according to him, after the paper of John Nash, the existence of an equilibrium in mixed strategies, this is the most remarkable paper. That's what he said. My next student was Marvin Trout. He was a graduate student simultaneously preparing for an actuarial job. His interest was in developing computer games for children, an effort in one of the early stages of pre-computer days. Since he had also taken my graduate course on games and statistical decisions, he was keen on developing algorithms for games on the unit square. The theorems of Carlin and Shapley, Bohnen, Carlin and Shapley, all found applications to statistical decisions through Blackwell's notion of S games. Can you move on to what is it called? Yeah. Now consider the following simple game. You have a set S, and two players play the following game. Player 1 chooses either the X coordinate or Y coordinate secretly. Player 2 chooses a point secretly inside the set. Once these two are done, player 1 receives from player 2 the coordinate which he has chosen of that point. So the question is, are there good strategies to play such a game? This is closely related to statistical decision problem, and Blackwell had proved several theorems. And one of the important things is, can you push it? Go to the, yeah. Okay. Trout's thesis solves these games where, no, can you go to the previous page? No. Just a minute. Yeah. These games completely, the value and player 2's good strategy are obtained, etc. When the end so you could have thought, you can go to this one. The other one. Yeah. In the padam.
It's there. They can see it.
Yeah, they can see that. Okay. Now consider the same kind of question where the set S is not formed a priori. It's formed by the use of n polynomials, P1t, P2, 2p, and t, for t in the interval 0 to 1. T in the interval 0 to 1. Now, given this, the problem now reduces to finding a good collection of t's. And he proved, actually Blackwell had proved, that you can choose finitely many t's, in fact at most n t's, and still mix them in a random fashion according to a fixed probability distribution and get the value. And this, he solved all such problems completely as part of his PhD thesis. And at the same time, we were thinking of applying for research grants from the Air Force of Scientific Research. One day he came and said that he showed this etch and sketch game where the two knobs, the left knob and the right knob, are controlled by two different players, player 1 and player 2. The one knob can, when you turn it, it can only move a point inside along the x-axis. The other one along the y-axis, player 2's. Now, player 2 is holding. Yeah. So in this picture, player 2 is actually trying to, suppose the point is here. It can move like this. Player 2 can push it up or down. He can pull in either direction. But player 1, he can go only like this. The moment he hits either this or this, the opponent's land is destroyed. So how to play such a game? This is more meaningful more than for the Air Force, for the naval. And the Air Force office was willing to actually support me with a research grant for the next 5 years to work on such problems. Yeah, okay. So it was a brilliant suggestion by Marvin Trout to design such a differential game using a game called the Etch and Sketch. I expressed my deep sense of gratitude. Unfortunately, he is no more. He passed away a few years back, and I don't have also any picture of him. He turned out to be one of the brilliant research workers at Kent State University, and he had at least 10 PhD students under him. Okay. My next student was Eugene Vasilescu. Okay, let me start with a simple example of what is called a NIM game. You have 3 baskets. Basket 1 has 10 apples. Basket 2 has 11 apples. Basket 3 has 16 apples. Players 1 and 2 take turns to choose a non-empty basket and remove as many as they want. Once a basket is empty, you have to choose only one of the non-empty baskets. Now, the issue is the person who is responsible for finally emptying all the baskets, namely the last basket to be emptied, is the winner. The question is, how do you play this game? What is a strategy? This was analyzed by Boughton even before any game theory was started. This was one of the earliest papers in the Annals of Mathematics in 1904. கொஞ்சம் மேல this guy Vasilescu was a new immigrant from Romania with an excellent mathematics background. He was keen on doing his PhD, but unable to take regular course requirements as he was a full-time worker for the Chicago Northwestern Railways as a hardcore computer programmer. He was willing to work in the theory of extensive games because I thought there are only a few papers, at most a dozen papers, in the 1970s. So he could take one of those papers and get a problem. So each week he would come once a week to present papers in extensive games by Zermelo, Dalkey, Kuhn, Otter, Dunn, and so on. He was willing to take a prelim exam in mathematical logic and algebraic topology because it was a necessary condition before you can do your PhD. You can start working on a thesis. Purely based on his earlier training from Romania, our department head, Professor Louis Hay, herself a logician, was excited to give him such a prelim, which he aced with flying colors, not only in mathematical logic, same way it happened also in algebraic topology given by Pete Bousfield. Famous British number theorist B.J. Birch had a paper on extensive games in the Proceedings of the Cambridge Philosophical Society, and I wanted Vasilescu to present that paper. And in fact, it was that work which became the main source for his thesis. Von Neumann formalized extensive games with information sets. Kuhn extended von Neumann's theorem on zero-sum 2% games with perfect information to non-zero-sum n% games with perfect information, incorporating the notion of Nash equilibria in pure strategies. In such games, all players are allowed to watch what each player chose in their earlier moves that has led to the move of the current player. Of course, they need to remember them. In such a case, there always exists a pre-established plan for each player who cannot strictly improve unilaterally, while the rest of the players stay put with their pre-established plan. Dalkey and independently Otter and Dunn proved that such a pre-established plan exists as long as each player can remember the choices with past moves of all the other players, while one could even forget one's own past moves and chance moves. A game has almost complete information if every player has complete information about his opponents, namely when you are playing the game, you are always you are nosy on what others have done, and you are allowed to nose. Whereas you may forget what you did in the past. That can happen. This question is, a game is said to be strictly determined for a particular player if the game admits an equilibrium where the player is simply sticking to a suitable pure strategy, whatever be the payoff. A game structure is strictly determined if it is strictly determined for each player. Dalkey proved that every game with almost complete information is strictly determined. The converse of this theorem is still open. We are not able to make any progress on this. Vasilescu's main contribution in this direction is a careful extension of this converse question that was first attacked by B.J. Birch. That a completely inflated game structure be strictly determined for player I. Further, for any two mutually overlapping information sets, for example, in this picture, the picture on the right side, you are seeing, say, player 3 starts the game. He can go left or right. When he goes left, then player 1 is informed that you are either at this point, I have to chemically tell him. Huh? Just okay. Either at this point, and from the the player 1 knows that it is either here or here. That means that is all the information he knows. So, namely, he was not sure whether he is making the next move immediately after 3 made a left choice, or 3 made a right choice and player 2 made a left choice, and after that he is coming. So these are called overlapping information sets. So these overlapping information sets are also coming one after the other for the player. But if that is the case, in this case, he settled that this condition is necessary and sufficient. That was his PhD thesis work, which runs into at least 20 pages of proof. Okay. Go to the next one. Next. Okay, yeah. Okay. Now I want to show something called almost complete information. Givama. Yes.
Yogi here.
Yeah.
Can you see me?
Can you see me? No, camera is not direct.
Camera is there.
Yeah. I can.
You will now give his case.
So can you see me?
Yeah, I can see you.
Okay, so actually that they had a plan for sightseeing today. So can you continue tomorrow?
No, but then it will take some time to finish it.
So how long it will take for you?
Now, how much time I have now? I have taken.
How long it will take?
Now what is the time?
5:30.
Yeah, your time was up to 5:30. And
5:30.
10 more minutes you take.
Yeah, so then okay.
10
So
more minutes.
if you
I
are
want,
in
then I may take a longer time tomorrow.
so 10 minutes is it okay?
Yeah, 10 seconds. I can now finish this portion.
Yeah.
Okay,
No.
then continue tomorrow again. You can continue tomorrow.
Yeah.
So you can finish this person.
Today there is some problem with the internet also.
So it is frequently going out.
Yeah.
Internet. So if that you can complete this person.
I will finish. Just forget about this picture. Go to the next one.
Okay.
No, it is extremely difficult. Okay. Go down. Go down.
So tell him that time is.
Now this is where I will stop with this one. Okay.
Okay.
The year 1975-76 was my first sabbatical year, and with my family, I went and I lectured on stochastic games at several research centers in Australia. I came to Monash University in Melbourne and as an external examiner for Pilar's master's thesis. Pilar was keen on joining me to work on stochastic games as his PhD thesis advisor at UIC. By then, T. Parsarthi, with now as P and R, Parsarthi and Raghavan, we had proved order field property for single control stochastic games, and so he wanted to come and work with me in 1976. And you push down one more. On the advice of Professor C.R. Rao, I joined ISI New Delhi as a visiting professor as a newly emerging campus with abstract courses. In my course on the theory of games and statistical decisions, I noticed Bapat as a scholarly-looking student who used to hear someone playing Hindustani classical music on bamboo flute, and my colleagues mentioned he is none other than Bapat. I was also preparing a notes on non-negative matrices and positive operators based on my thesis research. I wanted Bapat to help me in the proof correction of these notes. While doing proof correction, he drastically simplified many steps with alternative proofs. Unlike Philar from Australia, he too also wanted to come and work with me for his PhD under my guidance. The department at UIC had strict rules for foreign students to get their master's degree at UIC. Needless to say, both Bapat and Philar completed this requirement in the first year, and amidst tough interdepartmental competition across UIC, they both got the prestigious university-wide fellowship thanks to the special efforts by Professor Hedayat. I think I will stop here, and then tomorrow I can start with what.
So tomorrow you are planning to start with what?
Start with the Philar's work and Bapat's work, and then continue with the others.
So you are the PhD thesis of Pilar. PhD thesis advisor of Pilar.
Yes.
So you supervised PhD thesis of Pilar.
Yes. PhD thesis of Pilar, and then Bapat. They both came at the same time. So they finished just a few months apart.
I remember that we had a copy of Pilar's thesis, so I preserved it carefully. That it's a very well written thesis. I mean, nicely. I mean, the style we even copied. That so I didn't because the first page was not there. I didn't know that who was the supervisor. So glad to know that you are the supervisor.
Yeah. In fact, what happened was when I was giving lectures in Stanford, Arthur Weinert was asking me, where did you learn stochastic games? Did you learn from Philar's book? Then I opened the first page where he thanks me for inspiring him into stochastic games.
Because his thesis was given by T. Parthasarathi to me to look at it, and her first page was not there. So I didn't even know who was his supervisor.
Yeah. Okay. Very good. So I can start from tomorrow on that.
On that Philar's work, and then
okay.
And then your that.
Then I will talk about Bapat's.
So Ivansky, that you had that girl student.
Then after that, I invite Shapley for multi-choice cooperative games of Giroux, and then comes Zamir, then comes Solimosi. So many people, there are at least another 8 students.
So and another lady student who was struggling with the thesis. What is her name?
John Hardwick.
Okay.
Brian Powers, John Hardwick. Brian Powers came and gave talk also in ISI, in IIT Bombay, also in IIM Ahmedabad, in IA in Madras, and then I will show some pictures, etc., on the last day.
Okay. So at what time we will continue tomorrow?
3. Okay, 3, sir. 3 o'clock in the.
So we will continue at 3 o'clock. Okay.
Yeah.
So the session, that session is that after lunch session is from 2 to
2 to 3:40.
Then, yeah, by 3:10, actually, I started.
So 3:10.
Yes.
So you can join at 3:10.
3:10 means please send me the American time.
Okay. They will convert it so that according to your
But-
location, that.
That's okay. Because I was ready to talk at the right time, but Shivakumar was talking. That's fine. It's fine.
So how is your health now?
My health is fine, and I'm very busy with too many things, even with music and other things.
I sent you a mail that I didn't get a reply.
No, that I will reply later.
So that's why that I thought that you are prompt than me. So what has happened really? So I know that
There are too many things happening here. Today itself, I have tons of different things to do.
So Tagras is so went on very well.
Yeah.
Okay.
Yeah. Okay.
So this time we didn't see the videos.
No, I'll send you.
Okay.
Thank you.
You can send us the link.
Yeah.
Okay, so continue.
Yeah. Yeah.
Ma'am, you would like to
Okay.
say? Thank you, thank you, sir, and thank you, Sashmita Barik, ma'am, for actually chairing this session. Now we have come up to the end of this first day session. So we have whoever has registered for the trip, actually can join with us. And 7:30 is the dinner, and I'm
So are you hopeful that you will be able to come at right time?
maybe 8 o'clock will be back. That's the plan.
Others will be brought.
Guest house.
Then-
Okay, yeah.
So, but now we are not.
No, people from there can come to dining place directly.
So participants actually can come to the dinner place directly. There may not be a bus actually for picking up you right now, meaning after the around 7:40.
Okay, you are going there? I want some know by the way you are what you are saying, I'm not.
For the excursion?
People who are going out, they are coming directly. The people who are here around will not be picked up. Till 8 o'clock. Let me be very clear about.
So I thought of that the talking to you.
Hello, sir.
Suddenly,
Don't look at the board, look at the camera.
thought of talking to you. Suddenly you vanished from the skin.
Hello, Professor Neyogi. How are you?
I'm fine. So
Oh, nice to see you. And Krishnamurti and Manjunath, Professor Raghavan, all. Hello, how are you?
my wife is also here.
Yeah.
Can you recognize her?
Seeing you after a long time.
Here, ma'am. This side. Camera.
Hello.
So you recognize
How
her?
are you?
This side, then they can.
So you recognize her?
Yeah. How are you?
I'm fine.
Yeah.
So how are you, Professor?
I'm fine. I'm with my son in US now for a vacation.
So
Hello?
Hello.
I'm not able to hear you.
So it is younger son? You are with
Yeah, my eldest son, Gautam.
Elder son.
Yeah.
Yeah.
He's at Washington DC. Yeah.
Okay. I still.
Yeah. Nice.
Okay.
Where is Krishnamurti? I saw Krishnamurti.
Krishnamurti is here.
Hello. How are you? Yeah.
I thought her talk is there.
Yeah. Hello. I'm not able to hear you.
So your talk is tomorrow, right?
No,
Yeah.
not tomorrow.
Day after tomorrow.
Yeah. 7.
Okay. So
How are you? Good to see you.
I'm fine. Yeah. What are you doing?
Yeah, good to see you.
Oh, yeah.
Yeah, some messages we exchanged some time back, and then I'm yet to.
Yeah, sure. Yeah. Yeah. Yeah.
Yeah. So I thought
Nice to.
you would come here. I mean, I said Delhi conference also. I thought you would come and we would meet, and that was also online. Now also,
Yeah.
but yeah, hope to meet sometime soon.
Good. Nice seeing you all.
Yeah, nice seeing you.
Yeah.
Okay, sir. Yeah, thank you.
Yeah, this is without looking at the camera. Yeah, you want the face cards? No, I will focus here. Not like that. Why? You should. ಅಲ್ಲ ಕೂತ್ಕೊಳ್ಳಿ ಮಧ್ಯದಲ್ಲೇ ಮಧ್ಯದಲ್ಲೇ ಕೂತ್ಕೊಳ್ಳಿ ಅಲ್ಲೇ ಕೂತ್ಕೊಳ್ಳಿ ಅಥವಾ ಮೇಲ್ಗಡೆ ಕೂರಿಸಿ ಏನಿಲ್ಲ ಕಾಲಿನ ಸೋಸೋದು ಆಗ ಶೇರ್ ಮಾಡ್ಲಿಕ್ಕೆ access ಕೊಡು ಸೇವ್ ಮಾಡೋದು Yeah, it is asking you to sit on the dial. Yes, the percentage is correct. Yeah, it's okay. Anand Ellur is there, no? Yeah. So can you share your screen, please?
Good evening, everyone. A warm welcome to all of you to the session of contributory talks organized as part of Icords 2025, organized by Karen Smahi Manipal, taking place here at KEF R&D Center, MIT Manipal. It is my privilege to introduce the chairperson for the session, Dr. Vinay Madhusudanan, Assistant Professor, MIT Manipal. He has made significant contributions in the field of algebra and graph theory, and we are honored to have him chair the session. I now invite Dr. Vinay to take over the session.
Thank you very much. So the first speaker for the session is Mr. Anand Ellur from SDM Institute for Management Development, Mysuru, India. So I request the speaker to turn on the video if possible. As well as unmute yourself. Mr. Anand Ellur, are you there? Have you put him up? Okay.
Sorry, sir. Can I start now?
Yeah. So again, welcome, Mr. Anand Ellur.
Yes, sir. Thank you, sir.
First talk is exploring future research on the use of technology in project management, a morphological analysis. So I invite you to start.
Thank you, sir. Sir, mine is a short presentation because I had started this research just when Mahe called for this conference. So I'll just introduce the topic and then the work which I've done till now. So introduction is about how I just wanted to explore what technologies are being used in project management. So that's why I thought of working on this topic, which is exploring future research work on the use of technology in project management. I wanted to use morphological analysis in understanding what research gaps exist in the work which has been done in the area of using technology in project management. So we know that project management area itself is undergoing radical transformation in the sense there's a huge transformation like Mr. Andrew Ramdale says that it is going to change the entire this thing because of introduction of AI in different areas of project management. So I thought of just looking at how things are changing in project management area. So how things are planned, monitored, and executed with the introduction of AI and related fields, technologies in this area. So I wanted to use morphological analysis approach in order to understand what research work academicians are taking up with regards to the use of technology in project management. Of course, there is a huge radical transformation going on in real world project management. But what exactly academicians are working on with respect to technologies? Is it really matching or not? So I just wanted to do kind of mapping, understand what research gaps exist as of now. So whole idea about morphological analysis is that it tries to explain the underexplored explored or gaps, research gaps, in a very scientific manner, in a very detailed manner. So that's a use of morphological analysis, and it is very powerful tool in understanding the research gaps. So I thought of using morphological analysis rather than using very surface level systematic literature review. Morphological analysis gives better view of research gaps that exist. So the first step, as we all know, that is to extract the different research articles which have been written in this area of use of technology in project management. So in order to extract these research articles, which if we try to get it from apps and softwares which are very costly ones, I thought of using open source, which is Hajing's Publish or Perish app, which helps us to download different research articles from different sources. In fact, we should actually have API in order to download these papers, at least the titles, not exactly the papers. We can't extract the entire paper, but titles and abstract can be extracted using Publish or Perish app. So I started using this, and I got a good result. Hope you can see the screen here. This I've just downloaded few things from Scopus, Semantic Scholar, and Cross Reference. Of course, you can see the number of papers which it has helped me to download, but in fact, in the sense the titles, not the papers. But this is a huge chunk, in fact. So we'll have to filter it down later on. So the second stage is about the filtering process of these research articles. So that's the cleaning process. So in order to do that, we just have to check out which are all the duplicate titles which exist in the downloaded article titles, and then remove those duplicates, and then have around maybe the research work which literature which I have read is what it says is that around 1,000 papers would be a good number of research articles in order to carry out morphological analysis. I'm in the process of downloading those many, at least the abstracts, which will help us to develop this Zwicky box, which is nothing but morphological box. And a morphological box typically looks like this. Okay, the research articles will help us to identify different areas on which we can concentrate, which are called as dimensions. And in each dimensions, we can pick up certain variables and check out which dimension, which variables have been covered in those titles which have been downloaded. So we have to go on putting tick marks if something is covered. I'm just showing a few dimensions here. Like this is not actual download thing. This is potential dimensions, which I can say that technology could be one potential dimension. In technology, the variables could be data analytics, automation tools, AI and ML tool. And in knowledge area, the knowledge areas covered could be risk management, communication, scheduling. Industries covered could be construction, IT, automobile, like this. So suppose if I pick the first paper, first title, and when I read the abstract, that abstract tells me that this paper has used artificial intelligence in automobile industry, and it takes care of risk management. I'll go on ticking those boxes actually, which means that these areas have been covered. We need not get into that. So it means that the unticked areas in the box, in Zwiki box, will be the research gaps which will help us to understand this is the area which we can concentrate on. So this is a Zwiki box, morphological matrix, where the unticked areas would be our research gaps, in fact. So for this to happen, I have to carry out, I have to read downloaded articles and then go on finding out which are all the areas which have been already covered. This is the exact process of carrying out this morphological approach in understanding the use of technology in project management works. So this is what is expected output from my works. That's it from my side. Thank you, sir.
Thank you for that presentation. So you have presented the methodology. Can you, do you have any results to show? For example, have you populated some of these boxes and
no, sir. No, as of now, no, sir. I'm just in the process of downloading the titles, actually, sir.
Right. So this is the preliminary work. Okay. Another
Yes.
that I have is, are you going to do correlation analysis on this, or what is the step after identifying the research gaps or ticking the boxes?
No, sir. I'll carry out such analysis, correlation analysis. Like what exactly correlation between will be, sir? Between which variables? Like?
Right. So this, the tick boxes and the untick boxes, it's like a 0-1 version of the covariance matrix, because having the actual correlation values, you're only showing whether it's 0 or not 0.
Correct, correct.
So then would the next step be finding the actual correlation values?
Yeah.
Okay.
You're right. You're right, sir.
Okay. Any questions from the audience? Yeah, there's a question.
Yeah, hello.
Yes, sir.
This type of analysis looks really interesting for finding research gaps. However, I was wondering what's the difference or similarities between other literature review techniques like bibliometric or co-occurrence analysis, where it is used for finding the trends, finding new emerging topics, or also, like Scopus has a lot of like extractable data. Even Web of Science has some like research horizon network where they show how connected the nodes are with each of the topics. So where is the advantage of morphological analysis over other literature review techniques, and how it's going to help?
Yes, sir, I feel morphological analysis, what it does is that here it becomes mandatory that I go through the titles, abstract, or if possible, complete papers, and then go on understanding what has already been covered. I don't think the other methods like systematic literature review and all those things will help to go in such detailed manner. That's the only difference I can see, actually, sir. It will systematic literature review papers I have gone through, which actually are very superficial in understanding. Maybe it will help us to know the number of citations and to a certain extent trends and all, but not exactly the detailed research gaps which exist.
Any follow? Okay. Any other questions from the audience? If not, we thank the speaker once again. Thank you for that interesting presentation.
Thank you, sir. Thank you very much, sir. I'll unshare, sir.
Yeah, please, you can. So the next speaker of the day is Caroline Vinci from VIT Chennai. Can you? Yes. Good evening, Caroline. So, is your can you show the video or will you just share the screen? Yeah, we can see your screen now. Yes.
Good afternoon.
I think your audio is not very clear. Can you check? There is some disturbance in the audio. We are not able to hear you properly.
Am I audible now, sir?
Yeah, now we can. So I'll just say the topic of the next presentation is embedding the structure of Kp minus Cp to the power n into some family of graphs and computing its optimal wire length. So I welcome you to start the presentation. You have 15 minutes for presentation and 5 minutes for
Good afternoon. The topic of presentation today is embedding the structure Kp minus Cp the whole power n into some family of graphs and computing its optimal wire length. My name is Caroline Vinci, and as a co-author, Dr. David Raj Michael will be contributing to this report. Contents of the slide: introduction to graph embedding, preliminaries, embedding the structure Kp minus Cp the whole power n into some family of graphs and computing its optimal wire length, and the references. Introduction to graph embedding. So the communication links and the pattern between each of the components in a computer system is called as an interconnection network. So these interconnection networks play a crucial role in areas like parallel architecture, computer architecture, VLSI design. So mathematically efficiently simulating an interconnection network and its parallel algorithms on different interconnection network is called as graph embedding. Standard parameters in VLSI designs are total wire length, routing conversion, dilation, area efficiency, and time criticality. Of these, area efficiency and total wire length will contribute to the quality of the design. So, how do we topologically represent an interconnection network and a graph? So, the components in an interconnection network are considered as the vertices of the graph. The communication link between these components are the edges of the graph, and the whole interconnection network itself is considered as a graph. Preliminaries. The definition of graph embedding. Let G and H be finite graphs. An embedding of G into H is a pair F comma P of F defined as follows, where F is a 1-1 mapping from the vertex set of G to the vertex set of the graph H, and PF is again a 1-1 mapping from the edge set of the graph G to the path PF of E, where this path is in the graph H between F of U and F of E. Now, this is an example where a cycle of 8 vertices is using the embedding function f1 of x is equal to x is embedded into a tree on 8 vertices. The next parameter is dilation. F is F being embedding from the graph G into the graph H. If E is going to be an edge in the graph G, then the length of the path in H is called the dilation of the edge E, denoted by df of E. Then the dilation value for that particular embedding is the maximum of all the dilation values that we have calculated for the edge. Now the dilation of the graph G comma H is going to be equal to, over different embeddings that I am wearing, the minimum dilation value will be the dilation of the graph G comma H. Dilation sum. The dilation sum of an embedding for an embedding F is nothing but the sum of for each of the edge in G we would have calculated a dilation. Now sum of all that is called as the dilation sum. Now the dilation sum of G into H is defined as you pick up the minimum dilation value over different embeddings, and that is considered as the dilation sum of G into H. Edge condition. F be an embedding of G into H. You take an edge E that belongs to the edge set of H. Then ECF of E is denoted as the number of edges x comma y of G, such that E is in the path PF of x comma y between f of x and f of y in H. In other words, the edge condition of an edge is nothing but the cardinality of the edge set, where this E is nothing but the path that is traced in H. Now, the edge so for each of the edges, we would have calculated the edge condition. So, the maximum amount all that is going to give us the edge condition for the particular embedding F. Now, the edge condition of G comma H is nothing but the minimum of over different embeddings. I'll grab the minimum one edge condition value. Now the edge condition sum is again for an embedding f. For each of the edges that I have calculated I have calculated the edge condition, and summing up all will give me the edge condition sum. And the edge condition sum of g into h is nothing but the minimum of ECF of g comma h. The Y-length of an embedding f of g into h is given by Y-length f of g comma h is going to be equal to the dilation sum and the congestion sum. Now the Y-length of g into h is defined as, so the Y-length will be again over different embeddings that I am varying. The minimum Y-length value will give me the Y-length of the graph g comma h. Now this is an example one. The last example was circle on 8 vertices is embedded into a tree on 8 vertices. Here the vertices 1 is mapped to the vertex 1 of graph G and H, and the edge 1 comma 2 in G is mapped to the path 1 comma 3 and 3 comma 2 in the graph H. Similarly, the blue edge, which is 7 and 8 in graph G, is mapped as 7 and 8 in H also. Now this is a table where the first column represents the edges of G, and the second column is representing the path in H, and the third column is the path length, and the edge condition values of H are denoted in the last column. And according to the table, the dilation, which is the maximum path length, will be 3, and the edge condition value of this F1 is going to be 2, and the Y length of F1 is going to be equal to 14. A second example, a cycle on 8 vertices is again embedded into a structure called a hypercube, where the function g of x is going to be mapped to x itself. Now the dilation of g is going to be 2, and the edge condition of g is going to be 2, and the Y length of g is going to be 10. The edge isoparametric problem. So for a graph G, I choose a subset J from the vertex set of the graph G, and Ij of J is nothing but set of all edges such that both the vertices connecting these edges belong to the vertex set of J itself. So given any positive integer k, Ij of k is going to be the maximum cardinality of the set Ij of J. An example, so you have, let us fix k to be equal to 3. So in this graph, if I'm choosing the 3 vertices that I'm going to choose as 1, 2, and 3, then the maximum subgraph, the subgraph that would be induced is having edges only 2. But whereas when I take the set 2, 4, and 5 with the same k to be equal to 3, the edges that are induced by these 3 vertices is going to be 3. So the number of maximum edges that is induced is 3. So for any k whose cardinality is going to be 3, the maximum edges that would be there would be 3. Convex edge cut. So an edge cut is said to be a convex edge cut if its removal gives 2 components such that both of the components are convex sets. Convex sets are nothing but if you choose any 2 points u and v in the set A, all shortest path between u and v lie in A. Now I have shown an example of a graph where S is a convex edge cut cutting the edges 4, 7, 5, 8 and 6, 9, and it divides the graph into 2 components where 7, 8, 9 is one component and 1 to 6 is another component. Now, when you see both the components, any vertex that you choose between these components, the shortest path between these vertices lie within the component itself. Whereas in the second example, the edge cut T, it cuts the edges and it has one component as 5 and 6 and another component has the remaining vertices, where the shortest path between any two vertices does not lie in the same component itself. It crosses over the different component. Congestion lemma. F being embedding of an arbitrary graph from G into H, then S is an edge cut of H such that the removal of this edges of S separates H into 2 components. Further, S satisfies the following conditions. So for every edge A comma B that I'm going to choose in the between the components, the path PF of has no edge in S. So for every that is one condition, and the second condition is for every edge that I'm choosing in the graph G with one vertex in one component and another vertex in another component, then PF of A comma B has exactly one edge in the edge cut S. Now, V of G1 and V of G2 are the optimal sets, meaning that in other words, the edges that edge set of G1 and edge set of G2 are the maximum subgraphs of G. In other words, they satisfy the edge isoparametric problem. Now, if all these three conditions are satisfied, then the edge condition EC of F is minimum for all embeddings that you're going to choose, and the edge condition value is given by the following theorem. The partition lemma. So F is an embedding, and let K E of H denote a collection of edges of H repeated exactly K times. Now S1, S2, SR be a partition of K of E of H such that each SI is an edge cut of H satisfying the conditions of condition lemma. Then the Y length value is nothing but the edge condition sum divided by the partition value. Structure Kp minus Cp the whole power n and its parameters, where P is odd and P is greater than or equal to 9. Now the structure Kp minus Cp is nothing but a complete graph of P vertices where a cycle alone of P vertices is removed. And the n represents the dimension. So if for the first dimension, a complete graph with the cycle removed is the first dimension, and the remaining dimensions are nothing but the Cartesian products of the previous dimensions. The general definition of Cartesian product of any two graphs is nothing but where the vertex set where any two vertices x0, y0 and u0, v0 are adjacent. If the first vertex are the same and the y0 and v0 are adjacent, or if y0 and v0 is equal and x0 and y0 is adjacent in G. The parameters of the structure Kp minus Cp the whole power n. The nodes will be P power n, the edges will be P power n into P minus 3 by 2 into n, and the regularity is P minus 3 into n, and the length of the shortest path is going to be 3. Now this is an example K11 where this is a complete graph from 11 vertices and the red edges indicate that the cycle that we are removing. So after removing the cycle and rearranging the graph, so we get a structure like this. So rearranging this graph respect to a numerical character called del sequence. So for the construction of the Cartesian products of K11 minus C11, we use this sequence called del sequence, and then the number of vertices is 11 power n, the number of edges is going to be 11 power n into 4n, and the regularity is going to be 8n. And for every dimension that you're seeing, there is an underlying grid of the previous dimension. And the next thing is the structure is induced by vertices of each row of H, which is isomorphic to the previous dimension. Structure Kp minus Cp the whole power n and its optimal embedding when P is odd and P is greater than or equal to 9. Now this is the edge isoparametric problem of the structure Kp minus Cp that is the whole power n that is solved. And the first structure that we're going to embed is a grid. A grid is nothing but a Cartesian product of two path graphs. And this is the y length of Kp minus Cp the whole power n embedded into a grid. This is an example where the red edges denote the edge cuts. So we have a horizontal edge cut and a vertical edge cut. So these edge cuts divide the graph into two. The next structure will be a triangular snake. A triangular snake TSK with K vertices is a graph created from a path by introducing new vertices UI between each pair of adjacent vertices Vi and Vi plus 1. Now the Y length value that we have computed is given by the following theorem, and this is an example where each of the graph is a C3 cycle, and the red edges are the edge cuts. The next structure is extended banana tree. An extended banana tree is represented P of R1, R2 and Rm, and S1, S2, Sm is a graph where one leaf from each of the R1, R2, Rm copies of the S1, S2, S star graphs is connected to a single root vertex, which is different from the vertices of the star graph. Now here is an example. So this is an extended banana tree where there are two copies of a star with 4 vertices and one copy of a star graph with 5 vertices. This is the Y length of embedding Kp minus Cp the whole power n into an extended banana tree. This is the structure that we have worked with, where it is where all the 3 copies of a star graph is attached to a single root vertex, and the blue ones are also the edge cuts, and the red ones are also different edge cuts. arbitrary fixed generalized banana tree. The rooted arbitrary fixed generalized banana tree with L copies, with L copies of C with the caterpillar graph is denoted by T of L comma G comma H. A caterpillar is nothing but a connected acyclic structure in which the spine or backbone is produced by eliminating the legs of the or vertices of degrees 1, and G and H corresponds to the spine and the leg vertices, leg number of vertices. Now here is an example where there are two copies of a caterpillar graph with 4 vertices on the spine and 6 vertices has its legs. Now this is the violence of embedding the structure Kp minus P the whole power n. We have got the results in cases. So the first case will be P congruent to 1 mod 4, and the second case will be P congruent to 3 mod 4 where n is odd. The third case is where n is even, and this result is coinciding with the result of case 1. And this is an example of the arbitrary fixed generalized banana tree. Case 1. This is of case 2. A generalized hook graph. So consider a mesh T1 Cartesian product T2 with T1 rows and T2 columns. By connecting each vertex of the first column of the first mesh with the corresponding first column of the remaining meshes, a graph that is created from L copies of M is known as the generalized hook and is represented by GP of T1 comma T2 comma L. Now this is now you have 3 mesh copies where each of them is a 3 cross 3 grid, where the first vertex is connected to the first vertex of this and the first vertex of this. So now the y length of Kp minus Ep the whole power n embedded into a generalized hook graph is given by the following theorem. These are the different edge cuts of the generalized hook graph. Now a bistar. So a star graph Sn is a complete bipartite graph. A bistar graph denoted by Bs of m comma n is a graph obtained from the star graph Sm comma Sn by joining the non-pentant vertices with an edge. So the number of vertices in Bs is m plus n. So the y-length value of Kp minus Ep embedded into a bistar is given by the following theorem. And this is the structure. Conclusion. So obtaining the optimal layout of Kp minus Cp the whole power n into the following families of graphs, which is grid, triangular, snake, variants of banana tree, generalized hook graph, and a bistar. So computing their optimal y-length using the optimal layout. These are the references. Thank you. Sir.
Yeah, thank you, Caroline, for the presentation.
Yes, sir.
Yes, so I'm asking about the future scope of this work because you considered here a particular family Kp minus Cp to the power n. So are you going to consider other families of graphs for this embedding or generalizing it to a different to some larger class?
Sir, 1 minute. Can I just connect to my earphones? I think I'm not listening to.
All right. Yeah. Sure. Sure. Yes. Can you hear me now?
Yes. Sorry. Can you repeat the question, sir?
Okay. So I was asking whether about the scope of this future scope of this work. So you have considered this family of graphs Kp minus Cp to the power n for embedding. Are you going to consider other families of graphs with similar properties, or are you going to generalize it to a larger class of graphs? Or
yes, sir. So yeah, extending the structure. The first future scope that I'm looking for is looking for more family of graphs that will be embedded in the structure Kp minus Cp. And also in 2024, there is also a paper regarding the Cartesian product of complete graphs. So that also, so here right now we have done only removing one cycle for P which is odd and P greater than or equal to. So maybe we can try for even P to be even, removing a cycle and building the Cartesian products of it. So these are the two future scopes.
Right. So then the question is why you have considered what is it that makes it possibly easier for the odd values, and what difficulty do you face when you consider the even values? Do you have any comment on that?
Yes, sir. So for the order Kp minus Cp, the whole power n, the H isoperimetric problem was already solved. So using that was a tool for us. So we used that theorem to solve our problem, whereas it will be embedded. So that because H isoperimetric problem itself is a different area of research. So any structure that we take, we first have to solve the H isoperimetric problem and then find graphs which could be embedded in that structure. So that is the so in future we are going to take any other structure. Say for example, if P is even, then we have to solve the EIP of those graphs, and then we have to find the other families of graphs that will be embedded.
Okay, thank you. Again, any question from the audience? If not, we thank the speaker, and I think that is it for the day. These two sessions are all we have to do. Thank you.
Well done, Chairman and audience.
Thank you.
Sir.
Thank you, Dr. Vinay, for actually chairing the session. And I'd like to thank all the audience extender for this session as well. And thank you so much, and we'll see you tomorrow morning. Thank you.
Thank you.